Good morning, everybody, and welcome to the global edition of my optics review. We're here in our studio, and we're here with our studio audience in Boston, Massachusetts, a stone's throw from the Charles River and the Meltzer Auditorium at Mass Ioneer. And we have potentially we've had 500 people register to attend. We actually had to close registration at 500, and so because that's the maximum number that the system will allow. Because we have 500 people who are supposed to automatically be muted, we can anticipate that we may be bothered by whoever is talking right now, and I don't know why there is a line on the screen right now. So, whoever just logged in, someone's, yeah. So, let's see here. Just, if we put me on mute, then you're not going to be able to hear the audios. But it is possible that we'll have to just shut the whole thing down if people do continue to talk. But let's try to keep it going. I'm going to see if I can get rid of that line. So pardon me, everybody, while I shut this down and then back in again. We're living and dying by the technology. Because I have a feeling it's only going to continue, but let's try. I'm going to end show. I'm going to, because the line is still there, I'm going to sign out of power. I'm going to check out of Zoom for a minute. I hope I can get myself back in. And
you don't have to, David. They just took it out.
Oh, they took out the drawing?
Yeah.
So, did somebody else draw that?
I believe so.
Oh, goodness. Okay. Isn't that exciting?
So to all our connections, please do not annotate. Thank you.
Please do not annotate. That's a new one. Okay. So, good. So now we have, okay. So anyway, back where were we? So, let's get right into it then. Although this is not formally a CME event, you should probably know that I'm going to be talking about at least some of my work at Rebion, and I'm also going to talk about the book that I sell, which my wife and I share about $3 a copy for each one of these books. So those of you who haven't seen the book, it's still out there on Amazon, and we never really knew how well it was going to do. But right around this time of year, it can get pretty high, at least in the ophthalmology space. And then, so I'm hoping to make today's into a podcast, but in case we can't make it, or into probably just a YouTube video, but in case we can't, I still have the podcast of the one that I did some years ago, and that one has all different jokes than today's. So, so if you so there will be at least some reason to look at the old one, and most of the optics, the light still bends the way that it did in 2004 or whenever that was. I set up a web page which needs to be updated to make it easy to access some of those materials. So I know that studying optics, this is kind of what optics looks like to many of you, is kind of what, and so that's why this person on ophthoquestions.com says last 2 weeks before the test, and many of you who are watching this are taking a test. Many of you aren't taking a test, but regardless, someone suggested getting our book. But I don't want optics to be like this. I want optics to be like this. And so I think that it is possible to gather hold of the concepts, and even though I have an engineering background, I try to forget all of that and actually a lot of this didn't make any sense to me either, but if I sort of break it down step by step and think about and try to work it out, then the concepts begin to make more sense to me. Now, for those, many of you who are taking a test, the board exams, it seems that there's a consistent consistent group of questions that come up, and so we've put together a top 10 optics topics to expect on any examination. And so we'll run down the top 10 list, as we should. So number 10 is surgically induced refractive errors. What?
Sorry, Dr. Hunter, they're saying that they can't see the slides, just your face.
They can't see the slides, just my face.
Can you switch the slide view?
That's what I want. I want them to just see my face. Let me just make sure I'm sharing content properly. Exactly.
He's telling them what it says.
Oh, that was because we logged out. Okay, so no wonder, well, all right, so let me back it up, and can you just get confirmation from out in the world that they now can see my screen? Oh, actually, I can see it right over here. There we go. All right, so this is what I was saying you think of when you do optics, and this is where we're trying to go with it. Now, I need for the studio audience to laugh extra loud at my jokes so that everybody else can think that they're funny. Okay, number 10, surgically induced refractive errors. Number 9, contact lens fitting. Number 8, U plus D equals V, where objects and images go. Should be able to do that. Number 7, causes of acquired refractive error. Number 6, accommodation questions. Number 5, the size of a scotoma on a tangent screen. Number 4, a Jackson cross cylinder and just the optics of that. Number 3, magnification of a telescope. Number 2, vertex distance questions. And the number 1 optics topic to expect if you're going to be taking a written board exam is Prentice's rule. Well, we're going to have to get to that today, aren't we? So each of these questions is we're going to be able to be covering, and in addition, so you should have received electronically a handout. You should have also received some test questions, and then one file that's a test question, and then one file that's the answers to the questions. So I may or may not have time to go through all those test questions today. I do sometimes have everyone take the quiz. Were there any handouts out there when you got here? Okay, so we're definitely not taking the written test here as a group, but I do have 10 questions in a handout that should have been emailed to everybody. If it wasn't, we can email it after the fact, and you can just get to us that way. So when I do give those tests, you should try to time yourself to take those 10 questions over 10 minutes, because those who are taking the OCAPs, the whole OCAP exam, it's not all optics, but it's you have a 10-minute tutorial, 135 minutes for 125 items, and then another 135 minutes for 125 items. You should be able to get through each question in about a minute, some faster than others, obviously, and the optics ones may take longer. So the way that we're going to go over this over the course of the day, and we have till about 2 o'clock, is we'll do basics, which include physical optics, vergence, and lenses. Then we'll talk about different topics in refraction, as listed here. The third group is other optics of note, including prisms, mirrors, and then practical matters, prescribing glasses, instruments, and then sort of the final thing is optics in the office, which is where we try to put it all together, what you've learned to actually help take care of patients, because that's what we ultimately want to do well. So the way that I've tried to structure my slides, because people can get kind of lost, or perhaps your mind starts to wander. You think about whether you're supposed to pick up the dry cleaning today, and so then you lose track of where you are. And I've noticed that like ESPN you see like what's coming up next, and like maybe it's a good time to go to the bathroom if you see the next topic is one you don't want to hear. So I've tried to do something similar on these slides. So for example, right now we're about to talk about physical optics, and so and then we'll go off into the different parts. So just to kind of keep everybody, it's a long day, so help you to see where we are, where things stand in the course of things. And so, so here we are back to more equations, right? And he just said he was going to, not make this really complicated. But by the end of the day, each of these equations is going to seem like, it's going to be like your friend. It's a way to help you to remember concepts and a way to put the concepts into perspective and sort of a shorthand. And I almost think of it as, I think of each equation as almost like a little poem, because it's just like a few little letters that tell a big story. So, but if you look at them all like this, that's when it gets scary, but taking them one at a time, it won't be nearly so bad. So let's then go into the basics, and as I say, we'll start with physical optics. So we want to talk about sort of how light works, and also these different aspects of how light waves or rays interact with each other. And what is light? Is light a wave? Is it a particle? Is it a ray? You can seem to hear about it different ways, but in terms of the physics of it all, there's no one property that explains what light is. So sometimes we'll talk about light as a wave, and sometimes as light we'll talk about photons, which are little just packets of energy. When we talk about light rays, that's when we're doing our U plus D equals V to figure out where light rays are artificial constructs that we just use for objects and images, but not a physical property of light. And so when we think of light as a wave, it's just a tiny little sliver in the full spectrum of electromagnetic energy that comes across the universe. A little thumbnail of a sliver here, somewhere in between infrared light and ultraviolet light. So we just happen to have photoreceptors that are able to pick up that energy and to convert it into something that's real to us. So when we look then at an individual wave, a wave has there's a certain distance between the peaks, so that's the wavelength, and then it crosses the line here with a certain number of times per second, and that's the frequency, and then it also has a orientation. Any one light wave has an orientation where it can be say vertically oriented or obliquely oriented, and so light coming from the sun is going to have lots of different the photons that are coming from the sun. The waves, I should say, each one's going to have a different orientation. So that's called unpolarized light. Now, if we take unpolarized light, that's a whole bunch of light waves coming from a source, all with different orientations, and pass them through this can actually be a metal grid that absorbs some of the light, but anyway, if only the horizontally oriented, say, light waves get through that, then that's polarized light. It looks to your eye just like normal light for the most part, but polarized light, all the waves are in the same orientation. And once you do that, then you can begin to manipulate light and do things with it. So, for example, if this light has gone through a horizontal polarizer, you can now pass it through a second horizontal polarizer, and all the light's going to pass through. But if you rotate this horizontal polarizer vertically, now all the light is blocked, and so nothing gets through. And so this is a polarizing filter, and we see that as we rotate it in different orientations, then it either blocks or passes the light. So manipulable light, and we can use that in polarized microscopy, for example. So in polarized microscopy, you have a light source, a polarizer, and then another polarizer crossed, and here you are looking into the opening in the microscope. And if we now put say a crystal in there, if that crystal has birefringent material, that's a material that slightly can change the orientation of polarized light, of polarization. Now a little bit of light will now come out vertically polarized, and so some of that's going to leak through the vertical polarizer, and when you look at it in a dark field, then the crystal will appear to light up on the dark background because of the birefringence that's changed the polarized light on the way through the polarizing filters. So I've actually, in my fellow project, when I was a fellow with Dr. Guyton, my fellow project was to see if we could take that polarized concept, because the fovea has birefringence, and to see if we could scan the fovea with polarized light and in order to identify eye fixation. And so it turned out that actually worked. And so I'm still working on my fellow project, but if you can scan the eye with polarized light, figure out where the eye is fixating, and from that you can detect binocular alignment if you scan both eyes at the same time. And so we've come up with a device that we call the Blink, and it can automatically detect strabismus, and it's so good at detecting strabismus, it detects microstrabismus that's associated with amblyopia. And so we're now actually selling this device, just starting to sell it in another few weeks. We'll be at APOS, so that's my financial disclosure, is that my fellowship project from 1991 may actually turn into something useful.
That's cool.
So that's polarized light. Next is coherent light. So the light has little waves, peaks and valleys, and if one light wave has peaks and valleys, that's nice. If all the light waves have the same peaks and valleys at the same time, then that light is referred to as coherent. So in the old days, before a laser, the way you would make two beams of coherent light is you'd pass the light through a slit and then pass it through a second slit where, through a second panel that had two slits. And so that way all the light coming out of this slit was coherent with the light coming out of this slit. So then what you can do is when two beams of coherent light interact with each other on a screen, then the peaks from one match up with the valleys from the other, you'll get a maximum. And where the peaks from where the two peaks line up together, you get a maximum. And where the peak from one hits the valley of another, you get a minimum. And so if you do that against a panel of light, you'll get something like this, which is called an interference fringe. Because where the peaks match, that's constructive interference. Where the peak matches the valley, that's destructive interference. And so some of you saw me testing this ahead of time. Since I did the last podcast, I've been searching the internet for any useful or interesting videos, and here's one that sort of demonstrates this better than I think the slide.
I create ripples with a single source. They travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there.
So that's constructive and destructive interference. You need coherent beams of coherent light to make interference happen. That concept has been used commercially in the past as a means of testing potential acuity in patients who had cataract. Because if you have a cataractous lens, but you can get light through it, but it's not good at forming an image. But if the image doesn't form until two beams of light have passed through the cataract and then they interact on the retina, then you create an interference fringe. And that's a potential acuity meter that once upon a time was used, but no longer it's been replaced by other approaches. So next we also use interference, constructive and destructive, in anti-reflection coatings on glasses, for example, because anytime light passes through some interface, a glass interface, at least some portion of that is going to be reflected. It's about 4% that gets reflected back. And so that's going to create glare and reflections off of glass. And so when you get glasses that have anti-reflection coatings, what does that mean? Well, an anti-reflection coating is actually just another layer on top of the glass. And so if you, so you actually would still then get your reflection off of the surface, but now you get another reflection off of the anti-reflection coating surface. And if it's a quarter wavelength thick, then the reflections will be a half wavelength apart. And so then you see here you get destructive interference so that there's no light reflected back and all the light gets through. You can sort of recognize that sometimes because each wavelength has to have a different thickness of coating on it. And so you'll sometimes can kind of recognize anti-reflection coatings because they'll have like a blue or greenish hue because they're not quite as good at reflecting those. And I found this guy on the internet who extols the benefits of anti-reflection coatings as follows.
That is the difference. The top pair will protect you from light shining in behind you and blinding you, and the bottom pair does not. Trust me, these are my actual glasses, and I can attest that I should have got the bottom pair with the coating.
So there you go. You could potentially have been blinded if you hadn't shown up for this lecture this morning and bought yourself some glasses without the anti-reflection coating. So the other place that we use coherence and thus interference is optical coherence tomography. And the way that that works is that the light that's passing through you have a beam of light, and it's some of it bounces off a reference mirror and some of it bounces off the retina. And then the light, when it comes back, there's two beams of light, and the light that goes through the retina gets slowed down just a little bit, and that little bit of slowing down on the way through and back correlates with the properties of the tissue that it's going through. And so you're using constructive and destructive interference by how much the light is slowed down or sped up. And I have this so here's one beam of light, and it's going off to reflect off of one mirror. The other one's reflecting off of another mirror. And then those two beams, where they interact here onto this screen, if they're out of sequence, then they're going to subtract. If they're the exact distance, you're either going to get an intensity, an increase or a decrease in intensity, depending on if it's constructive or destructive interference, depending on how much the light is slowed down or sped up. And that's sort of the basics of how OCT works. I'll talk about other instruments more at the end of the day, but this one just seems so relevant to this that we stick it in here. So now this so the next concept is diffraction of physical optics, and that is what happens to light when it passes through a small aperture. Now, since you're ophthalmologists and you sort of know, well, intuitively you think that when light goes through a pinhole, it's going to be focused more sharply. And so if I ask you which one of these lights has gone through the smallest pinhole, you probably would think it's this bottom one, but actually it's the top set of lights that went through the smallest pinhole, because when pinholes get too small, you begin to get diffraction. That is, the light begins to bend and curve around the aperture. So our pinhole apertures that we use in visual acuity testing, those holes can only be so small that, yes, a little bit of a pinhole does shrink the blur circle on the retina, but if it gets too small, then you begin to get diffraction, and so then it's not going to be effective as a pinhole. And there's an optimal size for that. Also, in a patient who has very small pupils, a very small pupil will reduce the best visual acuity that a person can have, again, because of that diffraction that can take place. So here's an example of diffraction, again using water as a surrogate for light. The waves still behave the same way. And so the video, it's a little bumpy when it starts off, but you'll see that that there's an aperture here, and it's a small aperture. You'll see how far the waves spread, and then he'll enlarge the aperture, and when the water settles down after a second, then you'll see that the waves don't spread as far. So let's look at that.
Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave. more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced.
So smaller aperture makes more diffraction.
And if I were to make the aperture
We'll stop them
very
here.
wide,
So that's diffraction. So we've covered polarization, we've covered coherence, covered diffraction, and now we want to talk about scattering. So scattering is what happens to light when the light waves bounce off particles, little particles, for example, in air. Then they're going to be deflected, and so they're going to change direction. So when the light's traveling to us from the sun through open space, nothing happens, but when it hits the atmosphere, then we begin to get diffraction. And here's why blue light is diffracted more than red light, is scattered, I should say. Should I say diffracted? It's scattered. Here's why blue light is scattered more than red light.
You'll notice immediately that the blue photon is moving around a lot more in the same amount of space, and thus is scattered more. Every time one of those atmospheric particles glows, that's supposed to represent scattering. In real life, blue light is actually scattered by a factor of 6 times more.
So blue light scattered 6 times more than red light because it's higher energy blue light. It's hitting the air particles more often and getting deflected more often. And so when we're standing on the moon, the sky is black because nothing is getting scattered into our eyes. But when we're standing on Earth, the sky is blue because it's mostly the blue light that gets scattered into the eyes. And so, but the light coming from the sun, the blue part is mostly scattered out, and so the sun itself has a bit of a yellowish hue to it. Scattering also happens when we're trying to examine a patient who has asteroid hyalosis, as is shown here, and so the light from our slit lamp source, in this case, is getting scattered back to our eyes by those particles, and you might wonder how it's even possible that we can that the patient can see when you have this kind of intense reflection coming back to us. And the reason is that the source of the light is different for the patient than it is for us. So here we have a patient, if we have asteroid hyalosis, here are the little particles that are in the vitreous. The letter is over here that the patient's looking at, and as the light comes this way, the particles, they cast little shadows. They're called umbral cones, but they don't even make it to the retina, so it doesn't disturb the patient's vision at all, really. But when you put on your indirect ophthalmoscope, you're shining that bright light into the eye. These particles are scattering the light back to you, and so that's why you can't really see in when a patient has intense asteroid hyalosis. The only way to be able to see in would be to put the light source sort of inside the patient's eye, which you could do, for example, in a fluorescein, because in fluorescein you're shining in the blue light, but it's the green light that's coming back out. All the blue that's reflected or scattered back gets filtered out, and so so a fluorescein in a patient with asteroid hyalosis should be entirely normal. So then finally, in terms of physical optics, we're going to talk about refractive index. And refractive index is just has to do with how to characterize how light slows down when it enters a clear material that's not a vacuum. So here I have a beam of light, and the beam of light is coming towards this piece of plastic, and here's a piece of plastic. So when it enters this piece of plastic, it slows down, and the amount the ratio of how fast it goes in a vacuum to how much it slows down when it's in that material is the refractive index. Now, light can't go any faster than it goes in a vacuum, so the speed in the vacuum is always going to be faster than the speed in any material, so refractive index is always going to be higher than 1. And the more the light slows down, the higher the refractive index that you will see. So, for example, air doesn't have much of a refractive index because the light goes pretty much just as fast in air as it does in a vacuum. But water, it's slowed by about 33%, cornea 37%, lens 42%. the highest index materials that are available, that I know of anyway, will slow light down by about 80% compared to how it travels in a vacuum. So all of this slowing of light can have some consequences. So, for example, wait a second. So yes. So when the light is exactly perpendicular to the interface, or normal to the interface is perpendicular. So when the light enters this piece of plastic normal to the interface, all it does is, I'm trying to stay on my little camera, I'm supposed to be on a big camera, but anyway. So the light comes in, and then it goes in the glass, it slows down, and then it speeds back up again and leaves, and nothing else much interesting happens. But it gets interesting when the light comes into the plastic at an angle, because now not only does the light slow down, but it also changes direction. And it changes direction towards the normal to the interface when you go from low to high refractive index. So here is and so we don't have to draw all the little bars. We'll just draw the light as a single beam. So here's the light coming in. Here's the little dotted line is the normal to the interface. So light is bent towards the normal to the interface coming in. And then now if we turn the light around and go backwards, now we're going from high refractive index to low refractive index. Then the light's going to go away from the normal to the interface. So notice that in the left and the right image, the light's following the same pathway. It doesn't, regardless, but it's always being bent towards the normal to the interface from low to high, away from the normal interface from high to low. So it gets even more interesting then when you're going from high to low refractive index when you start to increase this angle. So let's see here. Here we've increased the angle some, and so now you're going even further away from the normal to the interface. And here we've increased the angle more, and we're going even further away. And now right here, you've got it to where the light is just skimming along the interface, and this is called the critical angle, and you can calculate the critical angle depending on the refractive index. For ordinary glass, it's 41 degrees. So when light is coming from high to low refractive index at 41 degrees, then it just comes skimming along the surface of the interface. And then it gets even more interesting when you get greater than the critical angle, because when you're greater than the critical angle, now none of the light can escape. It's stuck inside of the high refractive index material. So where does that matter in ophthalmology? Well, before we get to that, I found, you may have heard this of the science guy, but you may not have heard of the engineer guy. So the engineer guy is going to show us what you can do with total internal reflection. That this is a bucket full of, I think, propylene glycol, which has a refractive index of 1.4. And so you're going from high to low refractive index at greater than the critical angle. So we're going to pour light into a bucket. He loves it.
That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection.
So the other place we see total internal reflection is when we're trying to look into the angle of the eye, into the angle structures, because as the light is leaving the eye, and we're over here trying to look at it, it's going through high refractive index material, aqueous, and then it goes through cornea, and then it goes through tears, and then you hit this tear-air interface, and if the light's coming out at this angle and you're sitting over here trying to look at it, then you're going to get total internal reflection, and thus you actually can't see into the angle of an ordinary human being. And so the gonioscopy is a way to work around that, because now what you're doing is you're replacing that tear-air interface with tear-goniosol plastic interface. Then you hit this mirror, and so now you make it all the way through to the mirror. The mirror changes the angle, and now you see you're going from high to low interface at less than the critical angle, so now the light can escape, and therefore you can see the angle structures. I've actually tried to look and see if I could see angle structures, but you really can't. And the reason I have a cat there is that gonioscopy was actually discovered in a patient who had a very steep corneal degeneration, and so if the cornea is very steep, then over here, the cornea is very steep, then the light is going to exit at less than the critical angle it can get out. So human corneas aren't steep enough, and so I got to thinking that maybe cats' corneas are steep enough. So this is Buttons, and we tried to to see if we could get a look into Buttons' angle, but the experiment didn't go very well. As for some reason, she wasn't as interested in optics as in the birds outside. But I think right at the end here, I feel like you can almost see angle structures. Can we see them there? Maybe. Oh, too late. But anyway, you get the idea. But with the Kepi lens, that gives a nice steep angle. So the Kepi lens has no mirror in it. It just steepens the angle. So now we can definitely see angle structures there. So that's total internal reflection. And that is all that I know about physical optics. So given that we've now exhausted everything I know about physical optics, we'll just have to move on to talking about vergence and refraction and how things get refracted and objects and images and to our favorite U plus D equals V stuff. So let's go through first talking about what I actually mean by vergence. So now we're going to be talking about light as rays instead of as waves or particles. And so when light rays convert, and light always, my animation went off here. I was fussing with this last night. So light travels from left to right across the screen. So when rays of light converge, they're said to have plus vergence. When they diverge, they're said to have minus vergence. And when the rays of light, as they travel from left to right across the screen, are parallel, they're said to have zero vergence. So that sounds simple enough. Plus vergence, minus vergence, zero vergence. And so then, but we want to be able to put a number, like how much vergence is there? Like how much vergence do these light rays have? And is that different than these light rays, which seem to be diverging more? But actually, the vergence isn't any measure of this angle. It's the reciprocal of the distance to the point where light rays would intersect. So, let's see here. I sort of have to, let me see if I can do this, and there we go. Sort of like so. All right, so we can, when the light rays intersect, that's where an object or an image is formed. And so as we get to be 1 meter away, for example, then the reciprocal of 1 meter is 1 diopter. And these are diverging rays of light, so it's minus 1 diopter is the vergence at this point. But any one ray of light, any one object, the vergence of the light emerging from that object is going to continuously change as you get further and further away from that point. So it's not the angle, it's the distance away from the point of intersection, the reciprocal of that number that gives you the vergence. So here's some rays of light that some external system has created, and you see that they're converging on the way in, and then they reach this point. That's where the image is formed, and then they diverge on the way out. So what's the vergence of this light? Again, I think I made it through the whole first or maybe second, maybe even into the third year of residency, not understanding that the vergence actually changes. But here we are 1 meter away. It's converging light, so that's going to be 1 divided by 1 meter is 1 diopter. And then here we're a half a meter away here, so that's 1 divided by 0.5 meters. is two diopters. It's converging light, so it's plus vergence. And then 1/4 meter away, it's going to be 4 diopters. 1/10 of a meter away, 10th diopters. 1/millionth of a meter away from the point of intersection will be 1,000,000 diopters. That's exciting. And then at the point of intersection, it's infinite diopters of vergence. And then you go from positive infinity to negative infinity, and then you come out the other side and it's negative 1,000,000 diopters and negative 100,000 diopters and negative 4 diopters, minus 2 diopters. Here we are 1 meter away, minus 1 diopters, and 10 meters away, way down in the restroom over there, would be about 1/10 of a diopter of vergence. So that's vergence. So then, what do lenses do? Lenses just change the vergence of light. That's the job of a lens. So if you have a plus lens, it's going to take parallel rays of light, which have 0 vergence, and it's going to add positive vergence, and so that would make them converge. A minus lens will take parallel rays of light and make them diverge. So they'll reduce the vergence. So this then gets us to the point where we can do the basic lens formula, which is that the vergence entering the light plus the vergence added by the lens equals the vergence leaving the light. That is, U plus D equals V. The vergence entering plus the vergence added by the lens equals the vergence leaving the lens. So let's get right to a sample question to try to solve to see if we know where the object is. We know that we have a lens that's 2 meters away from the object. We know that the power of the lens is +2. So where's the image? Well, first we need to know, we got to get to U plus D equals V. So we need to know what's the power, what's the vergence entering the lens. And so to do that, we're 2 meters away, so we want to take a reciprocal. So 1 divided by 2 meters is 0.5 diopters. And it's minus 0.5 diopters because it's diverging light. And this is where we come to my first rule of optics, which is, when in doubt, take a reciprocal. So here we are, we're looking at this question, we're not sure what to do. We know we've got to take a reciprocal of something. So you could take a reciprocal, it happens that they both happen to be 2, so that's even better. But so now you have 0.5, and so then eventually you do have to figure something out, but now you're on your way, 0.5 minus 0.5. So now U plus D equals V, negative 0.5 plus 2 is positive 1.5. So the vergence leaving the lens is positive 1.5. So how far away is it from the lens? Take a reciprocal. 1 divided by 1.5 diopters is 0.67 meters. But where is it? Is it to the right or to the left? Well, it's positive vergence leaving the lens, so it must be over to the right. So it's to the right of the lens. It's 0.67 meters away. So there we have it. We know that the image is 0.67 meters away from the lens, or 2.67 meters away from the object, when we have a +2 lens. So this is one of the, and I guess here in the room we did just get a handout of the questions. Does the questions have the answers, or they don't have the answers? So they don't have the answers. So we're not necessarily going to have time to go through all of these questions, but maybe we'll do just one more of these just to kind of get the hang of it. So I'll help you with this one. So it's a -3 diopter lens. It's separated from -2 diopter lens by 25 centimeters. An object is 100 centimeters in front of the -3 diopter lens. An observer located behind the -2 lens will perceive the object where? So, and then you have to figure that out. So, the reason I wanted to just go through this first is, and you didn't have a chance to think about it, is there may be a little bit of a moment of panic here, because there's a lot of lenses in a lot of places and numbers. And so you just got to say, okay, well, I know I got to take a reciprocal of something, but before I do that, let me just figure out where the lenses are. So you draw a -3 diopter lens, and then you draw a -2 diopter lens, and you put them 25 centimeters apart. Like so. Okay, that's getting more familiar. And now it says that an object is 100 centimeters in front of the -3 diopter lens. Okay, so we'll put an object there, and we'll say that it's 100 centimeters in front. So, okay, there we go. So, we're
As if optics has been hard enough.
yeah. Unfortunately, I don't have, we had a glitch that I don't have host mode, so I can't just, I can't kick people off the island here. So, I can turn down the audio for me, but then you can't hear me, so that's not going to work. So an object is 100 centimeters away, so that's the number we want to take the reciprocal of, 100 centimeters, but we don't take a reciprocal of 100, we want to take a reciprocal of 1 meter, right? 100 centimeters is 1 meter, and so that's going to be 1 diopter. And then we do U plus D equals V, -1 plus -3 is -4. So the vergence exiting this lens is -4. So this means that the light leaving the lens is diverging. So then where are the rays of light going to come together? If they're diverging as they come this way? Well, we have to create imaginary extensions of the rays of light back to a point of intersection somewhere to the left of this lens. And how far away is it? It's 1 divided by 4 diopters, or 25 centimeters, to the left of the lens. So now there's nothing magical about light. Light has to first go through the first lens and then go through the second lens. And that's what we're doing. So now we've just gone through the first lens. So now we have to figure out what's going to happen to the light in the second lens. And so we can take as far as this lens goes, it doesn't know what the light went through to get there. So the image of the first lens becomes the object of the second lens. And so that object, since it was 25 centimeters away from the first lens, then we know that the distance from here to there is 25, and we said at the beginning of the equation that there's another 25 centimeters here. So the total distance is 50 centimeters away. So now our new U, our new light entering the lens, is 1 divided by 0.5 meters, right? Because we don't want to divide by centimeters. And I've done that. I don't know. I will say my OCAP scores in my first couple of years were not very good. Maybe I thought I knew it because I was an engineer, how I can figure this out. But anyway, convert to meters. 1 divided by 0.5 meters is 2 diopters. It's still diverging light, because remember, it was diverging light on the way out because we had to create imaginary extensions back to the point of intersection on the other side of the lens. So -2, now we do another U plus D equals V. -2 plus -2 is -4. So now the light leaving this lens, yes, 1 plus 5Z. Interesting. That's who's showing up as speaking. But I don't think they're listening to me. I have a sense that person's not riveted to my explanation here. So -4 diopters, so it's going to be diverging light. So again, we have to create imaginary extensions back to a point of intersection somewhere to the left of the lens. How far away is it? Take a reciprocal. 1/4 diopters is 0.25 meters, is 25 centimeters to the left of the lens. So it turns out in this particular problem, the image of the second lens is exactly where the first lens is. So back to our multiple choice question, the answer is that the image is at the plane, be perceived as being at the plane of the -3 lens. So these things now I could continue to work through these problems and you wouldn't get anything more out of it. So that's one of the reasons I wrote that book, was to just give people a bunch of problems so you can just work through them, and eventually you get the hang of it. It's just one of those things that you can do, and it starts to make sense. So I've been talking about objects and images and imaginary extensions, and so what does that all mean exactly, or why is that relevant? It does come up and can be handy sometimes if we just stop and take a second to think about object rays and image rays. So the object rays, the incoming rays are always going to be the left of the lens, and the outgoing rays are always going to be the right of the lens. That's fine. But the image, even if the image rays are to the right of the lens, the image might be to the right of the lens, but the image may be to the left of the lens. So the image space can be anywhere. Same with the object. The object rays are always to the left of the lens, but the object space, if you will, could be anywhere. So let me show you some examples of what I mean. So here is an object. The rays of light are coming out of the object. These are the object rays. The objects are on the same side. So that's a real object. Here, the rays are coming out this side. The image is on the same side the image itself is on the same side as the rays define it. So that's a real image. Now in this next example, here we have the diverging rays coming out. So we have to create imaginary extension of the rays of light back to a point of intersection somewhere on the other side of the lens. So that image is on the opposite side of the rays that define it. So that's a virtual image. So a virtual image is on the opposite side of the rays that define it. And same is true of you can also have a virtual object, real, virtual. So here's a object rays, always to the left of the lens, but where's the object itself? It's nowhere to the left here. We have to now create imaginary extensions to the other side, so this is a virtual object to the right of this lens. So that's real versus virtual, is just the virtual is on the opposite side of the rays that define it, but the object rays are always to the left, the image rays are always to the right. So I've talked about how light kind of gets slowed down when it enters the surface, and then it also changes direction when it's at an angle, and that's really what a lens does. But in a lens, like the rays of light coming at the top here are going to get bent downward, and coming up this way are going to get bent upward, assuming that this is the higher refractive index. But if the higher refractive index is over here, then the rays are going to go in the opposite direction. And so when we have a spherical surface, and we need to know if it's plus or minus power, the key is to understand which side has the higher refractive index. So we have to draw a little box around the interface like so. And if we color in the side that has the higher refractive index, now you can use your sort of intuition to see, oh, if n prime is higher, then this must be a minus lens. Or it must be this surface must be a negative refractive surface. But if n is the higher number, then this must be a positive plus lens at this interface. So here we are then with a plus. Now I've made n higher. That's the plus lens is higher. Here comes the rays of light coming in, and then those are going to be converged down to a point by this plus lens. And this n prime minus, the higher the refractive index, the more the light is slowed down at that interface, then the more power you're going to get for the same curvature. So the curvature is the radius of curvature. The smaller that radius, the shorter that line, the more curved the lens is going to be. So the only two pieces of information you need to know how strong a lens is one is how curved is the lens. That makes sense. We all know a more curved lens is going to be stronger. But the other thing is, what's the difference in index of refraction across the interface? And we can build that concept into a poem, that is a equation, which is that the power of a refracted spherical surface is equal to n prime minus n, the difference in refractive index, divided by r, the radius of curvature of the surface in meters. So d equals n prime minus n over r. That's not the last time you'll hear me say that today. So let's look at an example. We know the front surface of the cornea is a plus power, but what about that little back surface of the cornea where you go from cornea to aqueous. Is that a plus lens, or does that add even more plus power, or does that subtract power away from the light coming through? Well, you see it there already. Let's color in the side that has the higher refractive index. So cornea's refractive index is 1.37, aqueous is 1.33, so cornea gets the slight edge, so we color in the cornea side, and whoop, there it is, it's a minus lens. So it's minus lens power on the back surface of the cornea. So then how much power is coming off the back of the cornea? Well, and in fact, how much is on the front of the cornea? We should be able to figure both of those out. So, but on the back of the cornea, we just said d equals n prime minus n over r, so that's 1.37 minus 1.33. Radius of curvature of the cornea, it's about 7 millimeters. You see, sometimes I'll say 7 or 8, depending on how I want the arithmetic to work out, but it's 7, so 0.007 meters. So 1.37 minus 1.33 divided by 0.007 meters is, 5.7 diopters, and we already know it's a minus lens. So it's minus 5 or 6 diopters subtracted off of the front of the cornea when light passes through the cornea. So, because remember, we already worked out that it's minus power. How does that compare to the front of the cornea? We should be able to use this same formula to figure out this power of the front surface of the cornea. And so we just need a different refractive index. So now the refractive index of cornea, we already have that, it's 1.37, but now it's an air cornea interface, so it's 1.37 minus 1 divided by 0.007 meters. So the front surface of the cornea has a refractive power of plus 52.9 diopters, so that combination is going to be 52.9 minus 5.7, which is like 48 or so, which is close to what we think of a cornea as normally. We think of it as about 45. So, I could tweak the arithmetic and make it work out perfectly, but you get the idea. So then, why is it when we go underwater, we can't see? It's just so hard to see when you open your eyes underwater. It's all so foggy. Well, let's calculate the power of our cornea underwater. Because what's happening is when you go underwater, you're taking away the air cornea interface. So now on the front of the cornea is now, instead of 1.37 minus 1 on the front of the cornea divided by r, it's 1.37 minus 1.33 divided by r. So now the front of your cornea, when you open your eyes underwater, only has plus 5.7 diopters. Then you subtract the 5.7 diopters, I got getting excited, off of the back of the cornea, you end up with 0 power. It's as if you're halfway through an open sky vitrectomy. When you open your eyes underwater, you have no corneal power. You're a 45 diopter hyperope. So that would make it hard to see. So what is it when we put on our goggles? Are those 45 diopter, 48 diopter lenses in there? No, they're just replacing the water cornea interface with the normal air cornea interface, so you get back your refractive power of the front surface of your cornea. So then, if we were to take a plastic lens, and a really strong plastic lens, like a 50 diopter plastic lens, and dunk that into molten plastic, that lens would now have no power, right? Because you've completely lost now n prime minus n equals 0. So or I could actually tell you right now that I'm actually holding an air lens right here. It's a really strong one too, but because there's no interface, it doesn't have much power. So that becomes an issue not for doing silly things like that, but if you take a 20 diopter lens and you put it into the aqueous of the eye, an intraocular lens, and put it inside the eye, is it still a 20 diopter lens? No, it's going to be less power because now you're just at a aqueous plastic interface. So we can calculate that and answer this question. If the power of an intraocular lens is marked as 20 diopters inside the eye, what would be the power in air if you were to put it in your lens meter and dial it in? So we can use our n prime minus n over r formula, except we just divide the n prime minus n over r in air divided by the n prime minus n over r in plastic, and then r falls out of the equation. And so that way there's, which makes sense because the radius of curvature doesn't change whether it's in air or water, so you shouldn't need that number. Again, that's the nice thing about these formulas is they tell a story. But so here, so you have d in air is n prime minus n of IOL minus air, divided by the power in aqueous is n prime minus n in aqueous. And so that sort of sets up our formula. So now what do we know of these? We know the power in aqueous is 20. We know the refractive index of plastic is 1.49. We know the refractive index of air is 1 and of aqueous is 1.33. So then it's 1.49 minus 1, 1.49 was 33. Then we cross multiply and solve for air, and the number that comes out is 61 diopters. So that 20 diopter IOL, if you take it out of the package and stick it in a lens meter and read it, you'd measure it as 61 diopter lens. Except lens meters don't go that high, but details. So that's the basics of sort of the U plus D equals V part of things and the power of a spherical surface. So now let's move on to doing a little bit more of ray tracing, kind of just figuring out like how the eye works and focal points and that sort of thing. So focal points are a way to define another way to sort of describe the power and behavior of any one lens. So the primary focal point is the place where you would put an object so that parallel rays of light would emerge from a lens. So here is a plus lens, and you see that we would put an object about here, and then the U plus D equals V would end up as 0, so you'd end up with parallel rays coming out. Here's a minus lens. Its primary focal point is going to be a virtual focal point somewhere over there, because you got to put plus rays into a minus lens to get 0 to come out. So that's primary focal point. And so if we wanted to build a slide projector, we'd have a light source, then the slide would go here, and then the lens would go here so that parallel rays would come out and the light would be focused onto a screen off at infinity. Now, there's not just one point in space where that happens. There's a whole plane where you can have that happen. So here's the point here would get parallel rays coming out. A point here would have parallel rays coming out. Anywhere on this dotted line, you'd have parallel rays coming out. So that's the focal plane as opposed to the focal point. And that's the primary focal point. So you can also have a secondary focal point, and that's the place where when parallel rays are coming in, then the light is brought to a focus. So 0 going in, it's going to be just the reciprocal of the power of the lens. It's going to be that place where that happens. So the secondary focal point is where light is focused. So if you wanted to, say, take a magnifying glass and use it to burn things, then you would hold the magnifying glass. The distance would be the secondary focal point away, because then the parallel rays of light from the sun would be focused onto that one point into a high energy spot. So that's secondary focal points, and and here's another formula for you then. It's the focal length of a lens is the reciprocal of the power in diopters, which sort of makes sense, right? Because it's U plus D equals V, 0 plus power of the lens equals V, but then it's the reciprocal of that number coming out that's where the image is. So focal point is 1 divided by lens in diopters. So, for example, a 20 diopter lens, like the ones we use for indirect ophthalmoscopy, is going to have a focal length of 1 divided by 20, or 0.05 meters, or 5 centimeters. So if we want to burn leaves with our 20 diopter lens, we'd hold it about 5 centimeters away from the ground. A 3 diopter lens is a 33 centimeters focal length. The 1 diopter lens is a meter, etc. So this is so I work with some optical engineers in my other job, my night job, and if I tell them we need a 20 diopter lens, they're like, "What's that?" So it's like, "Oh, I need we need a 50 millimeter lens." Like, "Oh, 50 millimeter lens." Oh, okay. And so cameras, you hear about this 50 millimeter or 200 millimeter lens, whatever. It's just the focal length of the lenses. So now we did our U plus D equals V formula, but I have to say there is one thing we didn't think about, which is that we didn't talk about whether the image is upright or inverted. So in order to figure that out, we need to not just draw the object as a point, we have to give it some extra axial extension away like so. And so now what we can do is do ray tracing, and in particular we can draw the central ray. So the central ray goes from the tip of the object through the center of the lens, and like so. And it doesn't matter, is it a plus lens, is it a minus lens? You go from the center, from the tip of the object through the center of the lens. Then, turns out that any potential image is going to fall on the central ray, that the tip of the image that corresponds with the tip of the object has to fall on the central ray. So then we just do U plus D equals V, and we figure out where the image is. So let's say it's here. Then we just draw our line from the image to the central ray, and there we go. So now you can see that this image is inverted. What about if you have a minus lens? So here's our object. We draw our central ray. We do U plus D equals V. That tells us that the image is a virtual image somewhere over here. And so we draw a line. It has to be on the central ray, the tip of that image. So there we go. So now you can see that this image is upright. And also you can, furthermore, by drawing these rays, you can also tell that it's magnified. So that the image in this case is magnified. Here you can't tell, but if you actually draw this to scale on graph paper, if that's, you can figure out the magnification as well. And we'll get to magnification later. So central ray tells you where objects and images are. Now, when I was trying to, and so here's an object, here's a lens. I didn't say if it's plus or minus, but all the possible images are somewhere along here. Now, there's a way that you can, there's a way that you can also draw 3 rays to figure out where the image is, and that's called ray tracing. And unfortunately, the book that I chose to cram for optics before I took my boards only talked about ray tracing, and it didn't talk about this U plus D equals V. And so I found that really hard to understand, and so I got all those questions wrong. Well, for the OCAPs, I finally had it worked out in time. But there's 2 more lines that you draw. One goes through the primary focal point, and so you would go like from the tip of the object into the primary focal point and across, and then you go all the way across and then through the secondary focal point. And all 3 rays end up at the tip of the image. So, and you get the right distance and everything. So you can do these on graph paper if you want to, but I'm not going to support you in that. U plus D equals V works for me. So far, we've talked about all lenses as if they're magically thin and have no thickness of their own. But in real life, lenses do have thickness. And so we do have to make some adjustments to our formula to make that real. So here's a thick lens. And so what we're doing here is we're saying, well, instead of everything going through a single center, we have to say that it goes through these 2 nodal points, and the nodal points are separated by the thickness of the lens. So, in fact, our central ray goes from the tip of the object into the first nodal point, and then it jumps across and continues on at the same angle. Also, refraction occurs at these 2 principal planes on the front and back. And so when we're measuring U and V, so the U is the distance from the object to this first principal plane, and then you do U plus D equals V, and then you get your number, and that's going to come out of the second principal plane. So that's the jumping of the central ray. That's how we handle a thick lens. There's one other thing that we want to do, because what I'm working towards here is understanding how the eye works. And so there's one other thing I have to explain to you. Which is what happens when there is water or some other refractive index on one side of the lens and a different refractive index on the other side. So let's say you have air over here and aqueous over here. Well, the principal planes stay in the same place, but the nodal points get pulled into the side with the higher refractive index. And you say, this is awfully obscure. Well, some of you are saying this is awfully obscure, and some are saying, why does that happen? And for those who are saying, why does that happen? I'll say, I don't know. I haven't figured that out either. But the reason that it matters is when we want to know how the eye works, we need to know what's happening to the nodal points. So let's look at the eye then. So Gullstrand worked out the optics of the eye a long time ago and actually won the Nobel Prize in medicine for figuring this out, the optics of the eye. So, and it ties into all the concepts that we've just been talking about. So the eye is going to have a primary focal point. It's going to have a secondary focal point. It's going to have power, and that power happens to be somewhere near the cornea. It's going to have these two principal planes. It's got the nodal points that are pulled into the side here. So central rays are going to go through the nodal points. And then there's some numbers here that match up to the axial length of the eye. So these numbers are too complicated for us, right? Because we're trying to do infant optics. So we're going to make this a little simpler, and we're going to go with the reduced schematic eye, because we're not trying to win a Nobel Prize for this. So the reduced schematic eye, instead of saying that number, we say it's 60 diopters of power, and then that's going to give it a focal length of 17 millimeters, which is the reciprocal of 60. 1 divided by 60 is 0.17 meters. And then instead of saying it's got two principal planes near the cornea, we're going to say one principal plane right on the cornea. And then instead of saying two nodal points, those are really close together, we'll say it's got one nodal point. And but we can't really say the nodal points on the front of the cornea. We just can't get away with that. So we're saying it's 5.5 millimeters behind, which puts it 17 millimeters away from the secondary focal point, which falls exactly on the retina. So the axial length of the reduced schematic eye is going to be 17 plus 5.5, or 22.5 millimeters long. And so parallel rays of light coming in will be refracted here and will be focused onto the focal point of the secondary focal point of the eye, and that's the reduced schematic eye. So what are we going to do with that? Well, we can do a couple things. One is we can figure out how big images are that are projected onto the surface of the retina, and vice versa. So before we go figuring that out, I just want to remind you of some geometry, which is that similar triangles. So when you have two intersecting lines, those create similar triangles, and then the lengths of those, the ratios of these two are the same. So A divided by B equals X divided by Y. So let's use similar triangles to answer this question. What is the diameter of the blind spot when projected 2 meters from the eye, assuming that the optic disc diameter is 1.7 millimeters? So here's our model eye, our reduced schematic eye. We know you're actually supposed to remember this, that the nodal point is 17 millimeters away from the retina, which is 1 divided by 60 diopters, remember. And then we made it a little easier for you arithmetic-wise to say that this is 1.7 meters. So now we're saying it's projected 2 meters from the eye, so we're going to say that this distance from here to here is 2,000 millimeters. And the only thing we're missing is how tall is that? That's what we need to know. So we're going to redraw this without the eye there. So that's 2,000 meters. We got that 5.5 to get to the nodal point. It actually doesn't matter if you forget that, but anyway. So now we do similar triangles. 1.7 divided by 17 equals X divided by 2005. So then we cross multiply and solve for X, and we get 200 millimeters. So X is 200 millimeters tall, or 20 centimeters tall. So the blind spot projected out into space 2 meters away. If any of you ever seen tangent screens that they used to use for visual fields, you sit 20, if you have a tangent screen, they draw a little blind spot out on that, and if it's going to be 20 centimeters away for a testing distance of 2 meters, or it would be 10 centimeters tall for a testing distance of 1 meter. So we can also sort of figure things out the other way around and say if a patient has macular degeneration. How big is the scotoma going to be, for example? And so that might come up, and in fact, it does come up in one of your question 7, but we just sort of went through the arithmetic of that, so I'm not going to take the time to answer how big that is, but we do have this in the handout. So that's sort of the basics of optics. Remember, we did physical optics. I know it might seem like a long time ago, but we got through all that stuff: polarization, diffraction, scattering. And then we did vergence, light coming across. We've done lenses. We know how lenses work now. They're refracting the light, changing the angle because of the curvature of the lens, n prime minus n over r. So now we can move on to, like, how do we correct refractive error? And to get to that, we'll have to talk about visual acuity testing, and then we'll talk about refractive error and some of the nuances of correcting that. Now, I can just go all day. I don't even have to stop talking, but I've noticed that if I do that, people seem to I watch for what percentage of the eyes are open in the audience, and what percentage of people are having phone conversations on the, I forgot to turn off their microphone. But I do sort of need to, it's probably a good idea for us to take breaks from time to time. But if we take too many breaks, then we'll never get through the material. So what I propose is, let's just get through visual acuity testing, because it's going to wake you up anyway, and then we'll take a break. Okay, so we'll talk about visual angle, types of visual acuity, testing vision in children, briefly, and even though that's not really optics, but I like to talk about it anyway, and types of eye charts. So let's roll back to high school for a minute and remind you that 1 degree is 1/360th of a circle. And then if you take that 1 degree and blow it up, 1/60th of a degree is a minute of arc. And if we take that minute and blow it up, 1/60th of that minute is a second. So 1 second of arc is 1/60th of a 60th of a degree, which is 1/3600th of a degree is a second of arc of angle. So when we are assessing visual acuity, there's the minimum visible, minimum resolvable, and Vernier acuity. Minimum visible is just your ability to see a spot on the wall, an eye chart. You're trying to read the letters. You can't tell it's a letter, but you see a dot. You see there's 5 dots up there, say. That's your minimum visible acuity, and that's about 10 arc. You need about 10 seconds of arc of resolution to see that. To actually resolve a letter, you need about a minute of 1 arc minute of resolution to see that it's an E, the bars and the spaces between the lines of the E. So so that's 1 minute of arc, but our Vernier acuity is our highest precision acuity, and that's our ability to see a break in a line. Vernier acuity is, you can distinguish 2 to 3 seconds of arc of disparity, like so. Seeing the break in the line. And that's actually less than the separation of photoreceptors in our retina. We can even do that because of computations that our brain is making using putting the whole line into account. So our Vernier acuity is our finest acuity, and that's why we use it when we're turning knobs to line things up. It's better than just turning knobs to like make things focused or not focused. Those of you who used old manual cameras had a split screen focus in it, so you could use your Vernier acuity to do that. So I just mentioned that we need about 1 minute of arc to resolve the letters. So the 20/20E subtends 5 minutes of visual angle. It's on, the E, the space, the E, the space. Each of those subtends 1 minute of angle. So at 20 feet away, you'd need a 8.73 millimeter tall E is the 20/20E. That's what you're resolving to figure out what that letter is. So that means that we all know if you stand closer to the eye chart that you can see more of the letters, and that's because the 20/20E is subtending 5 minutes of visual angle. A 2200E then is obtaining 50 minutes of visual angle, so it's sort of linear. So a patient with 2200 acuity can read the 20/20 line from 2 feet away, because that's 2 divided by 200ths vision is the same as 2 divided by 20ths vision. 2 on the feet from the 20/20 line is 2200ths. So now in kids, we have, using various techniques, we can sort of get a sense of what their visual acuity is starting at birth. At birth, we don't really have much. They have a pupillary light reflex, they blink to light. We don't even really get an OKN response. Maybe you get it at birth, but you don't get really worried till if you don't see it till, say, 6 weeks. And then fixation and following movements, we don't see until maybe 2 to 4 weeks, and you get worried at about, somewhere between 6 weeks and 3 months, you start to worry about it. And so if someone says, checking a newborn in the nursery and they write down that they have fix and follow vision, it's like, oh, let's write a case report. A newborn with fix and follow vision. We do have ways, though, of quantifying visual responses in non-responsive kids. So these are the teller acuity cards, and kids will naturally gravitate towards looking at the side that has stripes on it, and you can use finer and finer stripes. And she's looking at the child sometimes through a peephole to see which way the child's looking, and eventually you can settle on a number. We use these a lot at children's. And and I should say, and then when kids get older, we can go into picture optotypes. And so these are the old Allen figures, and the problem with the Allen figures is that they blur to different shapes, and so even if you can't see them, you can tell they're different shapes. So clever kids can you'll just don't get as reliable a visual acuity with these. These are the Leia symbols, and I believe that, at least she told me she was, Leia Ivaranen is our special guest viewer. She's watching today, so thank you for the Leia symbols and for being a part of this lecture. So again, we just have the kids match the optotypes. We like to, the pictures, we like to get into letter optotypes as soon as we can, but the tumbling E has sort of fallen out of favor, I think, because it's really only 2 choices rather than 1, and it's easy if you get left-right confusion, then you end up with nothing. So we try to go from Leia symbols up to HOTV letters, and here he doesn't even have to say them out loud, he just has to do the match to get the letters. So now we have the old the standard Snellen or Sloan chart, but that has some pitfalls when it comes to doing research studies or trying to be consistent. So we have the ETDRS chart, or the Ferris-Bailey acuity chart, and these charts have letters of equal viewing difficulty. Each line has 5 letters. That's not true in the older style charts. The spacing between the letters is equal to the letter size on that line, and the optotypes change in 0.1 log unit increments, so that a 3-line change up here is the same as a 3-line change down there in terms of outcomes. So it's useful for research studies where you want to have your outcomes not dependent on what's on the variability that you have in these other types of eye charts. So what are some factors that can, other than disease, that can reduce the measured visual acuity? Because, say you're in an oral examination, you're in the optics section, and the patient has poor vision, you're probably not going to be being asked questions about macular degeneration. So the first thing to think about is maybe the patient needs a refraction. Well, how do you what's the diagnostic test for refractive error? Pinhole. Uncorrected ametropia. Pupil size, I already mentioned that a small pupil, and in the Academy books it says 2.5, so that's the number we know. So pupil less than 2.5, you're going to start getting diffraction and get reduction in visual acuity. But also a very large pupil, you start to expose some of the imperfections in the periphery of the lens and of the cornea. And so if the pupils are very large, you can get reduced vision. So like in the refractive surgery, studies are, they want the cycloplegic refraction, but then once you're doing a cycloplegic refraction, you're not necessarily going to get your best visual acuity, so you have to put like a little aperture in there, not a pinhole aperture, but an aperture to get your true acuity. So, and also in the office, if we've done a cycloplegic refraction on a child, but we can't get them to what they were before the drops went in, it's like, well, it's big pupils, so irregularities. And then poor contrast. So the eye chart or the lighting may not be optimal in your eye chart, so that could reduce your visual acuity measurement. And then very young patients, I just showed you, kids not going to expect to have normal vision, and then the elderly, we don't expect them to have perfect vision, even in the absence of disease as you get up in years. So why don't we then, before we launch into refractive error, so it's 9:35 Boston time, so let's take a 10-minute break or so, and then we will resume. All right. So we'll go through some definitions and then finish with, for that part, with vertex distance correction. So what is refractive error? Well, remember from the reduced schematic eye that 60 diopters puts the secondary focal point of the eye exactly on the retina, and that's with accommodation completely relaxed. And when the secondary focal point doesn't fall exactly onto the retina, then we have refractive error. So that can occur either because we can have myopia, either if the eye is too strong or too long. If the eye is too strong in front, then the focal point moves in front. If the eye is too long, then the retina goes behind. Or we can have hyperopia, either refractive if the eye is too weak, or axial if the eye is too short. So that's thinking about refractive error in the context of where the secondary focal point is, but we can also turn the light around and then project the light from the retina out into the world and sort of see where it goes that way, and that's the far point. So the far point of the eye in an emmetropic eye, this is going to be at the proper focal length, so you're going to have parallel rays of light emerging from the eye, so the far point will be at infinity. But if the eye is myopic, then again, think of the front of the eye as too strong, then the rays of light are going to come out, and instead of coming out parallel, there's too much power here, so they're going to be converging, so then the far point is somewhere in front of the eye. And the more myopic, the closer to the eye it is. In a hyperopic patient, the far point is the rays of light coming out are still diverging, so we have to create imaginary extension of the rays of light back to a point of intersection somewhere behind the eye. So the far point of a hyperopic eye is a virtual far point somewhere behind the eye. So that's why a hyperopic person, no matter if they have no accommodation, no matter how far or close they hold it in front of them, they're not going to be able to see it well. And so when you open your eyes underwater and you're 50 diopters of hyperopia, you cannot find any distance where the light's going to be in focus. So when we correct ametropia, then one way to think of it is we're taking a lens whose focal point coincides with the far point of the eye. And you might wonder why we are thinking of it that way, but it'll make sense when we talk about vertex distance, because it's not just the power of the lens that matters, it's the position of the lens that matters just as much. So here's a myopic eye. It has a far point somewhere. We're going to bring a lens in whose focal point coincides with the far point, and that will bring the light into focus on the retina. For a hyperopic eye, so that's the myopic eye. For a hyperopic eye, the far point somewhere behind the eye, but it's the same thing. We just take a plus lens, and we choose a plus lens whose focal point coincides with the far point. So you see then that this distance matters, and if we slide this lens forward, then the focal point's going to fall away from the far point, and it's no longer going to be an effective lens. So that's where lens effectivity comes into play. So here, for example, is a 10 diopter lens that's correcting this patient's refractive error. So what does that mean exactly? So the plus 10 lens, that means its focal point, which is 1 divided by 10, or 0.1 meters, or 10 centimeters, behind the lens coincides with the far point of the eye. So if we now slide the lens forward, further away from the eye, now those don't line up anymore. So we need a longer focal length to get back to the far point. So we're going to have to choose, say, a 9 diopter lens. 1 divided by 9 diopters is 0.11 meters, or 11.1 centimeters away. So it turns out that a 10 diopter lens at this distance corrects the same refractive error as a 9 diopter lens at this distance. And the further away for the plus lens that you get in front of the eye, the less plus power you need to correct refractive error. So you could actually you could correct this patient's refractive error with a +1 lens as long as you held it far enough away from the eye. So another way to think of this is, because we want to also have some intuitive sense of this, and you know that +10 spectacle lens, if that patient wanted contacts, you know that aphakic contacts tend to be higher, so that might be corrected by, say, a +15 contact lens. And you know intraocular lenses, they tend to be 18 or 20 diopters. And so intuitively, just from your clinical experience, you know that the closer you get to the retina, the higher plus power you need to correct the same refractive error. So, but we can do it intuitively, but we sometimes also have to do it mathematically. So this is a common problem. This is one of the top 10, I believe. A patient comes into the office with a 12.5 diopter spectacle lens at a 13 millimeter vertex distance. That's the distance from the back of the lens to the front of the cornea. They want to wear contact lenses. So what power contact lens do you expect would be necessary for this person? So we go to our first rule of optics. When in doubt, take a reciprocal. And there's only 2 numbers here. We don't think we're going to take the reciprocal of that one, so it's the 12.5. So 1 over 12.5 diopters is 8 centimeters. Then you're like, oh yes, 8 centimeter focal length, or 80 millimeters. That's how far it is to the far point of the eye. So now we want to move the lens closer to the far point of the eye. So that means we're going to take 80 millimeters minus 13 millimeters, and that's going to give us this number, which is 0.67 meters. So now we take another reciprocal. 1 divided by 0.67 meters is 15 diopters. And so the 12.5 spectacle lens corresponds with the 15 diopter contact lens. And you can do this with minus lenses too. You just have to remember that you're moving them to the far point somewhere in front of the eye. So there's some rules to read. So there's some. So for plus lenses, I just explained how when you move the plus lens forward, you get more effective plus power. So with minus lenses, it's kind of the same, but it's kind of the opposite. Because when you move minus lenses forward, you also get more plus power, but that means you get less minus power. So I have minus lenses. It's getting harder and harder for me to see you. They're getting less and less focused as I move these away like so. And then I get more and more effective minus power. So when someone wants to, a myopic person, if their glasses are sort of down in their eyes and they want to see something better, they'll push their glasses up on their nose, not just to get the better frame, but to get more effective minus power. So moving minus lenses towards the eye increases the effective minus power, decreases the effective plus power. So it's the same, but it's the opposite because you're starting at a different place. And so this is in your pretest that asks about correcting the it asks a vertex distance question, which we're not going to go through today, but I do have the answers, so you can read through those answers. So that's effective lens power of plus lenses and of minus lenses. And so next, let's go into talking about accommodation. And we'll talk about the physical properties of accommodation, and then how to measure it, and then prescribing bifocals. So humans can become presbyopic with age, as can monkeys. And so this is from a study, which I cite below, of long-sightedness, not in monkeys and apes, long-sightedness in old white bonobos during grooming. So you see, this is the younger ape, this is the older ape who's sitting much further away, and we can get their refractive error and plot their age against the distance that they are sitting away when they are grooming each other. So how does that happen? It happens by, the Helmholtz theory of accommodation is that the lens wants to be round, but the zonules are pulling on it. And so when we're focused at a distance, it's parallel rays of light coming into the eye. But when something is up close, it's no longer parallel rays of light coming in, so you need more power to get focused by the time you get to the retina. So here, this might have been on focus at the retina, but now here, it's focused somewhere behind the retina. So when the ciliary muscle contracts, the zonules relax, the lens gets rounder, it gets stronger, and so the light is focused onto the retina. And I found this this video demonstration talking about, because there are some accommodating IOLs that change their shape, not only their shape but their distance. And well, here, let's just watch this video.
As the ciliary body relaxes, zonules pull the haptics flat, moving the optic backwards. When the ciliary body contracts, the haptics vault the optic forward. In this way, the Z lens moves back and forth in much the same way that the natural lens does during accommodation and disaccommodation.
So you see, there's a little bit more to it than what I said, because it's not just the change of shape, but also the change of position within the eye getting further away from, the lens getting further away and closer to the retina. And as the plus lens gets further from the retina, you get more effective plus power. So you can get accommodation not just through change of shape, but change of position. So this and other accommodating lenses are using that to advantage somewhat to gain some accommodation, like a quarter diopter. Not as much as we might like to see. And then smaller apertures can also give you a better depth of focus. And so this is an intraocular lens that has an aperture inside of it to not only remove aberrations but also add to depth of focus. And that's another way to gain sort of pseudo accommodation. So we've talked about the far point already. That's the technically. Oh, somebody's scribbling on the screen. If you could, how long has that been there? It's getting worse. However, of the many hundreds of people who are watching, one of you has allowed your child to scribble on the screen, and if there's some way that you could remove that for the benefit of all, that would be great. Kids. So I don't know if there's some way to use peer pressure to somehow get those to go away. I could sign out and sign back in too. What do you think? No, just keep going. Okay. So so just as the far point is the point, oh, that's getting better, on the visual axis that's conjugate to the retina with accommodation completely relaxed, the near point is the point on the visual axis that's conjugate to the retina with accommodation fully active. So that's when you dial in all your accommodation, that's going to be your near point, the place that's in focus. So we can measure accommodation in two ways. We can talk about amplitude of accommodation, and we can talk about range of accommodation. So the amplitude of accommodation is the physical property of the lens to be able to change its shape and to shift focus. But the range of accommodation has to do with not just the change of shape of the lens, the physical property, but also whether you're underlying myopia or hyperopia. So to measure amplitude of accommodation, we can do it in the phoropter or not. We have this, there's this Prince rule that can stick into the phoropter, and it's marked off in diopters of power. And then we give the person their distance correction. We start with the distance correction, and then you slide this closer, 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 closer until it just starts to go out of focus, because as soon as it starts to blur on them, then they're no longer following it with their accommodation. And so at that point, if you have your distance correction in place and they've maximized their accommodation, then the reciprocal of that distance is going to be their accommodative amplitude. You do this one eye at a time. So you measure accommodation in the right eye first, and then the accommodative amplitude in the left eye. And again, if you don't have the distance correction in place, then you're going to have the wrong number, because if they're 3 diopters of myopia, then they're going to get a head start on their accommodation of 3 diopters. And in fact, in most people who are having trouble reading and having trouble with near function, even when you slide this all the way out to the end, at like a meter away, they may still have trouble focusing on it. So usually what we do is you put in the distance correction, but then you click in like another, say, 3 diopters. So then the starting point where their accommodation is fully relaxed is going to be 3 diopters away, or 1/3 of a meter away. And then you start moving it closer, 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 closer until it goes out of focus. So let's say they can go from 3 diopters with the +3 clicked in up to 4 diopters away, or 25 centimeters away. Then their amplitude of accommodation is going to be 1 diopter, because that's all they can dial in before it starts to blur. So once you know the amplitude of accommodation, then you can figure out the range of accommodation. And so, and again, I'll just remind, just in case the people who've drawn on their screens, everybody in the world is seeing those drawings, and there's nothing that I can do about it. If you're awake, then please do look and delete your annotation function. Thank you. So now we have an eye. Let's say we have an eye. We know that that eye has an 8 diopter amplitude of accommodation. What's the range of accommodation if that eye has 4 diopters of hyperopia? So they have 4 diopters of hyperopia. They have a far point, a virtual far point that's somewhere behind the eye. And we have to use up 4 diopters of accommodation just to get into focus at infinity. So use up 4 diopters, that puts you in focus at infinity. Now you got 4 diopters less left to be able to bring something in up close. So we dial in the extra 4 diopters. So your near point is going to be 1 divided by 4 diopters, or 25 centimeters away from the away. So your range of accommodation is from infinity up to 25 centimeters away. Now let's look at the same example with a 8 diopter, with a person who has 4 diopters of myopia and an 8 diopter amplitude of accommodation. So now, as I mentioned before, they have 4 diopters of myopia, so they sort of have built-in 4 diopters of accommodation, right? Because if I'm 4 diopters of myopia, everything's blurry out there, but it's nice and clear here with no effort, no accommodative effort expended. So now they've got that 4 diopter head start. They can put 8 diopters on top of that. So the total is 8 plus 4 is 12 diopters. 1 divided by 12 is 0.083 meters, or 8.3 centimeters away. So the range of accommodation, is from 25 centimeters up to 8.3 centimeters away for that 4 diopter myope. Now, if the 4 diopter myope puts on glasses, or the 4 diopter hyperope puts on 4 diopter glasses, they're both going to have a range of accommodation from infinity up to 1/8 of a meter away, because they have an 8 diopter amplitude of accommodation. That was how we measured it in the first place. But when you take the glasses off, the range of accommodation changes. So we have a patient in the office. They say they're having trouble reading. they're 45 years old and they describe difficulty focusing at near. So you're going to measure their accommodative amplitude in each eye and then calculate the range of accommodation, and then you're probably just going to give them some low power. You're going to just throw up some plus 125s and see if that's okay. And that's fine. Trial and error in the office, that's okay. You can get a little fancier without having to do all that. You can sort of assume that a 40-year-old is going to have 6 diopters and a 60-year-old is going to have 1 diopter of accommodation. And then you ask them, where do you like to hold things? So that's their working distance. Say they like to hold things 3 diopters away. So then they'd have to be expending 3 diopters. So they need a 3 diopter add, but you don't have to give it all to them. They can use some of their innate accommodation. So this 40-year-old, you generally want them to use about half of their accommodation. So the 40-year-old, this one, assuming they're not symptomatic, they probably don't need 3 diopters. They don't need anything. But this person, this 44-year-old, they have 4 diopters of accommodation. So you expect them to use 2. So 2's almost going to get you there, but you need maybe another 1 diopter. So then they need about a 1 diopter add, or the 125 add, which is what I told you to do in the first place. But anyway, so tables are okay. Trial and error is probably okay most of the time. But when the patient's getting their third opinion because they're miserable and they're unable to work so I've actually had, although I do strabismus, I've had patients who are like out of work because they can't, because of the strain and the stress, and somebody thinks it's strabismus, but it ends up being that they're presbyopic and they have trouble accommodating on their Bloomberg screens all day long. And a pair of glasses actually can help get patients back to work. So every now and then you actually do want to try to assess accommodation, and it can help you to get through some difficulties. So this one is another question. I think let's work through this one because I think it shows up from, all of these are in our top 10. So I've gave you 11 questions for the top 10 that we went through. So this is a 61-year-old man with proper distance correction. He has 1 diopter of accommodative amplitude. He's wearing trifocals with +3 near add and a +150 intermediate segment. While wearing the trifocals, A, objects at all distances are clear because of the trifocals. B, all objects are closer than 33 centimeters are blurred. C, objects between 40 and 33 are blurred. D, all objects beyond 67 are clear. E, all objects beyond 40 are clear. Well, what are we going to do about that? I don't know if we're going to need to take a reciprocal, probably. But we also want to draw, we've got like some facts here. So the patient has 1 diopter of accommodative amplitude. I think we need to draw a range of accommodation. So let's see without glasses what's in focus, right? So he's 1 diopter of accommodative amplitude. So we know he can go from infinity up to 1 diopter, which is 1 meter away, without using any bifocals when measuring. So let's draw it out like so. So we're from infinity up to 1 diopter away, which is 100 centimeters away. Now, when we go to the intermediate segment, that's a +150 diopter. So when he relaxes all accommodations, 1 divided by 1.50 diopters is 0.67 meters. But then when he dials in his full diopter, that's going to be up to 2.50, right? So he's going to go from 1.50 plus 1 more diopter on top of that. So that's 1 divided by 2.50 is 40 centimeters. And then when he goes down to the trifocal segment, the +3, 1 divided by 3 diopters is 33 centimeters. That's relaxing accommodation. Now he dials in that last diopter again on top of the 3, and that gets him up to 25 centimeters. So you see that he can go from infinity to 100 centimeters. He can go from 67 to 40, and he can go from 33 to 25, but it's blurry in between those all those spaces. So then we just have to work through the answers which ones make sense, and it says objects between 40 and 33 centimeters are blurred. That is correct. So what do you do? So perhaps this patient says he doesn't like his trifocals. Well, obviously this would be a case for considering a progressive ad, because then he can go have it focused anywhere. Or there might be other tricks that you could use, or separate computer glasses, or just something to try to give him more zones in which to work to try to be able to see clearly. So next, let's talk about astigmatism. So we'll talk about the definition of a cylindrical lens. And you know how I've not exactly joked about how I didn't understand most of this until like my final OCAPs, which I did pass. But I didn't understand astigmatism until I'd been giving this lecture for like 2 years. So, because I just borrowed Dave Guyton's slides and sort of talked through it. But these slides I made up on my own because I think I finally figured it out of what astigmatism is. I still can't explain it to patients. Maybe I should use these, this note. Just fire up the PowerPoint every time they say, "What's astigmatism?" So in order to understand astigmatism, what we have to do is imagine light not just as a beam of light or a ray of light, but to imagine that it's many infinite planes. It's an infinite number of planes of light, one next to the other, that are passing through a lens. And we can think of the planes as both vertical, but then we can also think of them as horizontal planes of light. So here we have a lens, and it's a cylindrical lens, and now you see why it's called a cylindrical lens, because it's a cylinder. I've cut it in half, but it's still half of a cylinder. So what happens to a vertical plane of light that wants to go through this lens? And I just have to walk through this. I can't explain this without walking, so I'm trying to do this like this. So a vertical plane of light is going to be coming along at the speed of light, and it hits the lens, slows down, and then it just comes right back through. No refraction happened because all it saw was just a vertical flat surface. So no refraction happens to any of the infinite vertical planes of light that come through. But a horizontal plane of light, it's going to see a curved surface. So it's going to get refracted to a point. And so is the horizontal plane of light above it, and so is the horizontal plane of light below it. And all the infinite planes of light get refracted to a single focal line that is parallel to the axis but perpendicular to the power of the lens. So that's basically what astigmatism takes: a single focal point and it breaks it out into two focal lines. In this case, the other focal line is off at infinity. So let's bring that other focal line in closer. We're going to add a curved surface to this lens. We're going to curve the vertical surface now too. So now the vertical plane sees a little, gets a little bit refracted, takes it longer to come to a point because it's a weaker lens, and the plane next to it and the plane next to it. So now you see we have a vertical focal line, we have a horizontal focal line. Each of those are perpendicular to the power, and then the vertical line becomes an ellipse, and then there's a circle, and then a horizontal ellipse, and then a horizontal line. So that distance between the two focal lines is called the interval of Sturm, and the shape that encompasses that's bounded by the aperture of the light coming in is called the conoid of Sturm. And this point in where it's a circle is called the circle of least confusion. So let's look at a video to demonstrate the Sturm's conoid, as John Jackson calls it.
So here is my image screen with my astigmatic system. And as you can see, if I move the screen to this position, I get a vertical line on the screen. And as I keep on going, I get to a circle on the screen. I keep pushing it back farther, I get a horizontal line on the screen. So those are my three marker locations inside Sturm's conoid. I have the line closest to the lens, the near line, the circle of least confusion, and then finally the far line. So that's what they look like on the big.
So that's it. Now you've seen it in real life. You don't have to imagine it anymore. And again, we almost didn't get through that thanks to the line that one of our hundreds of participants has chosen to draw on his screen. That's okay. I'm not particular about things. So just as the eye, a normal eye, has a single focal point, with a refractive error, you get a focal point that moves in front of it. With an astigmatic error, you have two focal lines that are in the two meridians. In this case, both focal lines are in front of the retina. And just as you can have a far point for an eye with refractive error, an astigmatic eye is going to have two far lines somewhere in front of or behind the retina. And just as you correct refractive error with a lens whose focal point matches the far point of the eye, you can choose an astigmatic lens whose two far lines match those two focal lines match the far lines of the retina. And when we're correcting astigmatism, it always just helps to kind of look at just to remind you that astigmatic lenses are symmetric. They're not symmetric, they're identical. So whether it's the right eye or the left eye, 30 degrees is always going to be here, right and left eye. And every 30 degrees is another clock hour on the eye. So, so this is 11 o'clock is going to be 120 degrees. So when we talk about astigmatic lenses, because we have 2 bits of information, we have to somehow plot that out or indicate it in some way. Well, 3 bits, there's two powers and an angle. And so we can do that with this cross diagram. So in this case, this is power cross, so it's 3 diopters acting in the 45 degree meridian and 1 diopter acting in the 135 degree meridian. We can also do it as an axis cross, because remember how I said that the axis of the lens is perpendicular to the power of the lens. The curvy part makes it into a line that goes the opposite way. So the axis cross is just going to be 45 degrees away from the power cross. So, this is yet another thing that pretty much all of residency I didn't get right. So I want to go through this. How do you go from a power cross to a glasses prescription? So here we have a power cross. We have a -1 in the 180 degree. We have a +2 in the 90 degree meridian. And so the first thing you can do is you can just, remember I drew it as just a cylindrical lens. You can imagine there's just 2 cylindrical lenses that are doing that. So you can take those apart, and here's one power cross with the +2 in the 90 degree meridian, and this is the combined with symbol, and then you have -1 in the 180 degree meridian, and that's one way to draw it. So then we can just write this down as numbers. This is +2 in the 90 degree meridian is +2 axis 180, and then -1 in the 180 meridian is -1 axis 90. So +2 axis 180 combined with -1 axis 90 is another way to describe this power cross. But that's still a little clunky. It's still not a glasses prescription. So what we need is spherocylindrical notation. So we have to take one of these numbers and make them into a sphere, and then compensate for that with the other number. So to do that, we can take, say, this lens, and we can add, imagine you're physically putting a little +2 cylindrical lens this way, and that's going to make this into a +2 sphere. But if you put a +2 lens here, you're going to have to put a -2 lens over here, because what we give to this side, we have to take away from this side so that the combination ends up the same. So that means we put a -2 here, so that's now it becomes a -3 over here. So now we can just add across, make sure we did it right. 0 + 2 is +2, good. -3 + 2 is -1, so that's good. So this is the same as this. So now we have +2 sphere combined with -3 in the 180 meridian, or +2 sphere combined with -3 axis 90. So that's spherocylindrical notation minus cylinder format. We could have done the same thing if we just made this one into the sphere. So this, we put a -1 here. We have to take -1 away from here. Or that is, put a +1 here. If we put a -1 here, we have to put a +1 here so that the combination is the same. So we put our -1 here, we put our +1 here, so the 2 becomes a 3. So that's -1 sphere combined with +3 axis 180. 90 degrees away from the power is the axis. So there's spherocylindrical minus cylinder form, here's spherocylindrical plus cylinder form, and we can convert between those, which I'll do in just a minute. So that sort of explains that. Now, we sometimes need to go the opposite way, and have some problems later that we'll get to that. So you can do that by, here's the prescription. You can draw 2 power crosses. There's +2 combined with -3 in the 90-degree meridian, which is -3 at 90 degrees, which is -3 in the 180 meridian. And then we just add across the meridians. So that's +2 plus 0 is +2, +2 minus 3 is -1, and we've worked our way back to the power cross there. Another way to do it is to write the prescription out in both plus and minus cylinder form. So to get from plus cylinder to minus cylinder, the new sphere is the old sphere plus the old cylinder. So +2 minus 3 is -1. The new cylinder is the same as the old cylinder, but with the opposite sign. And the new axis is 90 degrees away from the old axis. So these are the same prescription in minus and plus cylinder form. Then you just take, this was just something that sort of noticed just looking at the numbers. You take the +2 and you put it on the 90 degree meridian. And you take the -1 and you put it on the 180 degree meridian. And that's, so that way you can just go straight to a power cross, or you can just eyeball a prescription and say, oh, that's got +2 power in the 90 degree meridian. The final way to do it is you can, if once you get good at it, you can just sort of like do it in your head, and just like, especially in the original one that I showed you, when you're trying to go from this to a prescription, once you have practice, you can just say, oh, this is -1 plus 3 in the 90 degree meridian, -1 plus 3 to get there, axis 180. So you can do it in your head, but it's like, that's later, once you get the hang of it. You can do it this way by writing it out in plus and minus cylinder form. Tells you what are the 2 numbers that are going to go on to the power cross and where do they go. So this all then translate, we have to know how to do that when we're doing retinoscopy with free lenses, because in kids, that's what we don't get to use the phoropter that all the time. So in retinoscopy, we have our little intercept, and when we're neutralized, then we get the whole pupil fills with light. And so let's say you have a child who holds still enough that you can neutralize in this meridian, this horizontal meridian, with a +250 lens. So that is going to go, so you're sweeping the power, but the intercept of the retinoscope is marking your axis. So that's, if you've got +250 here, then you're going to go axis +250. And then you rotate it 90 degrees, and now you sweep across this way, and now let's say that neutralizes at 450, so then that means a 450 is going to go on this axis. That's an axis cross, not a power cross, because this is marking the axis, but you're sweeping across the power. So then now you've got to turn that into a glasses prescription. But so that's the gross retinoscopy is +250. Then it takes 2 more diopters to get there, so it's +250 plus 2. But now we're on an axis cross, so it's axis 90. But then we have to take our working distance, which we haven't talked about yet, but we subtract the reciprocal of distance that we were away from the patient. I guess we'll get to that later. And so that would be a 150, for me anyway, 0.67 meters. So that's our net prescription is -1 plus 2 times 90. Now, if you retinoscope with combined spherocylindrical lenses, you don't have to write down the two numbers and write it on the axis, but you don't always have that luxury. So that's how you go from retinoscopy with free lenses to a glasses prescription, which you should know how to do. Now, sometimes, again, in kids, they'll have really strong prescriptions, and we just want to like retinoscope over that to see if there's any change. And if it's a spherical change, that's easy. But when you have a cylindrical change, it can get complicated. So here he's got these thick lenses, and now we need, with cylinder in them, now we need more cylinder. How are we going to get this new prescription? Well, you could plug it into one of these online cylinder adding things, because it's a complicated, it's not something you can do in your head unless they happen to line up with, they line up with each other, great, but what if one's at, 160 and one's at 35, then that's harder to add those up, so you can put it in a calculator. But the other way to do it is to just take the whole thing, the glasses and the clip and the cylindrical lens, you put the whole thing in the lens meter, and then you just read it like any other unknown lens. So you can add cylinders if they more or less line up with each other, and sometimes when you're given a written question, they might like say one's at 180 and the other's at 170 or something, but for the purpose of those calculations, it's not a big deal. But what if we had something like this? We have two lenses, we have two power crosses, and we want to combine these two lenses. What do we end up with? So all we have to do is just add across the meridians. So we plus 450 plus 1 is plus 550, plus 1 plus 450 is plus 550. So you actually have a sphere. This combination of these two lenses gives you a plus 550 sphere. Now, there are different types of astigmatism. You may have seen that I alluded to compound myopic astigmatism earlier. That's where both of the focal lines are in front of the retina. And if both of the focal lines are behind the retina, that's compound hyperopic astigmatism. If one's in front and one's behind, that's mixed. And on occasion, one of the focal lines will fall on the retina. So that's either simple myopic, where the other one's in front, or simple hyperopic, where the other focal line is behind the lens. So these are the different types of astigmatism, compound myopic to compound hyperopic. And then we can also talk about astigmatism being with the rule or against the rule. And part of the reason is that some of us use plus cylinder notation and some use minus cylinder notation, and so it can sometimes get difficult to communicate, but with the rule is the same whether you use plus or minus cylinder. With the rule means the cornea is steeper in the vertical meridian. Against the rule means it's steeper in the horizontal meridian. This with the rule tends to be most common in young people. We tend to see more against the rule in older people. You can also define it by the axis of correcting cylinders. So with the rule, the axis is in the of plus cylinders is 90 degrees or close to 90. Which those of you who see kids a lot, we're sort of used to expecting to see that they're going to have the cylinder somewhere close to 90. We're always a little surprised when a kid has plus cylinder at 180, because it's just uncommon. If it's not within 20 degrees of one of these meridians, then we call it oblique astigmatism. So I have some examples here of refractions, which are, that I've written out. Like I might have just given it to you, this one, and ask you what kind of astigmatism is that. And to figure it out, you would now convert to minus cylinder and look at the two numbers. So plus 2 minus 3 times 90. We add the sphere plus the cylinder to get the new sphere. So plus 2 minus 3 is minus 1. The new cylinder is the opposite of the old cylinder. Change the sign, and the axis is 90 degrees away. So now we see one of the numbers on the power cross is a plus and one's a minus, so that's mixed astigmatism. But this one, plus 2 minus 2 times 90, when we write it out, new sphere is plus 2, minus 2 is 0. The old cylinder is plus, opposite sign, axis, etc. So now you see on the power cross, one's a plus 2, one's a plano, so that's simple hyperopic. And then here both the numbers are plus, so that's compound hyperopic astigmatism. when we're trying to prescribe glasses for kids, we actually will often calculate the spherical equivalent. Sometimes you just can't tell glancing at a prescription whether it's net hyperopic or net myopic if the numbers are opposites. So you have to calculate the spherical equivalent to decide whether you're correcting hyperopia or not. And then the spherical equivalent is sphere plus half cylinder. And so in this last case, it'd be sphere is 1, half cylinder is 1, would be 50. So this spherical equivalent of this one is plus 150. Spherical equivalent of this one is going to be plus 1. And when you put the spherical equivalent up there, you're not correcting the astigmatism, but at least you're putting the circle of least confusion on the retina. So one of the things that it's good to be able to do, if you like to do refractive surgery or even to prescribe contacts, is you want to be able to understand where whether you're dealing with the lenticular astigmatism or corneal astigmatism or some combination of the two. And one way to do that is to get keratometry and look at the keratometry numbers and make sure that they correspond with what you would expect in the prescription. So here's an example. You have a patient whose keratometry is 40 diopters in the 30-degree meridian and 46 diopters in the 120-degree meridian. So what sort of astigmatic correction do you expect would correct that refractive error in that person? So we know that there's a 6 diopter difference between meridians. So we would expect that the glasses prescription would have, to get them to good vision, would be about 6 diopters. Now, maybe not exactly 6 because of vertex distance considerations. It should be around 6 diopters. So then, what meridian, though, should it be in? So we see here that the 120-degree meridian is the steepest one. And so if you got 6 diopters too much at 120, you'd need to put -6 in the 120-degree meridian. So that's -6 axis 30. And so in that glasses prescription, you would expect to see some number sphere -6 axis 30. And if you don't see that, then there's more than corneal astigmatism going on. The easiest way to think of that is you can have a patient who has 2 diopters of cylinder in keratometry, but they're correctable to 20/20 with spherical lenses. Well, then you know they must have some sort of complementary lenticular astigmatism that matches things up. So what you don't want to do in a case like that is to do refractive surgery to take away their corneal astigmatism, because then you're just going to unmask their lenticular astigmatism and cause big trouble. So sometimes when we do our surgery, we sometimes we'll tie sutures down, and those sutures, if they're not tied to just the right tension, can cause astigmatism. So here we have a cornea there's been a corneal incision. The incision has been closed with the suture, perfect depth, nicely tied down. And if that suture is tied too tight, though, then that can create more astigmatism in the meridian of the suture. And so I've always thought it actually steepens the cornea, which you would think that if you tie a suture too tight, you'd think it would flatten the cornea, because like too tight should sort of flatten it. And it turns out that, and that confused me for a long time, and again, until this one I've been teaching for a couple of years too, before I've worked this out, is yes, where the suture is too tight, it gets flat, but then the rest of the cornea has a compensatory steepening because the distance overall, the circumference of the eye doesn't change. So it's as if somebody's putting their foot down on the edge of the cornea and flattening it at the edge, so then you're getting like a steepening in the rest of it. So, and where's the pupil here? The pupil is under the steep part. So that's why flattening in this periphery steepens it over the pupil. And so if that happens, you have to cut that suture to relax that suture, and that'll let it flatten out again in that meridian. And that's why a relaxing incision out here in this meridian will then actually steepen the periphery of the cornea and flatten it further in the center. So there are some different lens aberrations that are important in our day-to-day lives trying to do refractions, and those include spherical aberration and astigmatism of oblique incidence. So spherical aberration, so far when we've talked about lenses, whether they're thin or thick lenses, we've assumed that no matter where the light passes through, it's going to see the same power. But if you look at the curvature of this lens, you see it actually looks more curved out at the periphery than it is at the center. So these two rays passing through the center are going to see one power, but then the rays of light that pass through the periphery see a stronger power, and they come into focus in a different place. So this spherical aberration can cause halos, blurry vision, and imperfect vision. We can also see it when we do retinoscopy. I don't know if you sometimes, especially in kids, like I see this a lot in a child where you're doing your retinoscopy and there's still with motion in the middle, but there's like against motion in the periphery of the lens. And so then you put up more and more, then you put less, but then you got too much in the middle, so you put up more, but now you're getting all this against motion in the periphery. And so when you see that, you just have to remember that after dilation, the pupil is going to shrink down. So you want to neutralize the middle part of the lens. You ignore what's happening in the periphery. You've got to just neutralize the center of the lens when you see this spherical aberration. It's called positive spherical aberration when it's stronger in the periphery and negative when it's not. But we usually see positive spherical aberration in kids. So there are lenses that counteract spherical aberration that aren't this just by convex shape. And so the 20 diopter lenses that we use for indirect ophthalmoscopy, you'll see it says on the side aspheric, meaning that there's less spherical aberration. But it's only aspheric when you use it when the white ring's not showing. See what happens? This is just two lenses I took. I put them on an Amsler grid, and see how this one, the white, this is upside down. You can see the white ring and how much you get all this aberration here. But it's perfectly aspheric when you have the white ring down. Now, when you tilt a lens, I should make a video of this. When you tilt a lens, you can induce astigmatism in the axis of tilt. Oh, we've got a new yellow crayon now. And there's a dot here, a dot. There's little dots on the screen too. For some reason, the dots bother me the most. With the axis of tilt. So you induce cylinder with the axis of tilt. And again, you can actually sort of figure that out just by looking at this, that you see that it's getting steeper when you tilt it like this. So you're getting more like lens curvature inside of this span when it's tilted compared to when it's straight. So plus lens induces plus cylinder, minus lens induces minus cylinder. And as a result, when you do, for example, if you're trying to do retinoscopy,
honestly, I don't understand.
So, well, that's good. When you're trying to do retinoscopy, and especially in kids where a child has, say, a big esotropia, if you're retinoscoping that esotropic eye, you're going to get all this extra cylinder just from oblique, from this astigmatism of oblique incidence. So you have to make sure that you're on axis with the lens before you target it, before you retinoscope it. And also you can gain, if you wear glasses and you tilt your glasses, you can tell that you're inducing astigmatism, that things get kind of blurry if you tilt it a lot. Now, if you tilt it a little bit, then you also get a little bit of sphere, so you can gain a little bit of extra sphere before the astigmatism gets too bad. So you can feel like the glasses are getting a little stronger, but then the cylinder just overwhelms it. So sometimes undercorrected myopes will walk around with their glasses sort of tilted up on their side like that, on their ears like so. So let's do a differential diagnosis of acquired refractive error, because I think that's on the list too. So here's one that recently added to the lecture. This is a woman who's had blurry vision since her last eye exam. So Aubrey Gilbert gave me these slides. And you see, if you can see it past all the scribbles on the screen, that something's going on with her lens. It appears that her lens is in front of her iris. So that would give you, when the lens is in the anterior chamber, so the question, I guess, is she more myopic or is she more hyperopic now that her lens is in front of her iris? Well, you're getting more effective lens power, so she probably has had a big myopic shift. Here's a patient who has a lot of curvature on the front of his cornea. That looks like an awful lot. In fact, you can almost see his angle structures. This is a patient who has keratoconus. And so keratoconus can cause you to have a myopic shift because you're making the cornea too strong. Here's a child with big, beautiful eyes, but the eyes are big and beautiful because this child had congenital glaucoma, and the congenital glaucoma has caused axial elongation. So this patient has increasing myopia from axial elongation from uncontrolled glaucoma in childhood, and this child also had uncontrolled glaucoma in childhood, very myopic eyes. So what's the differential diagnosis then of someone who has acquired myopia? Well, it's things that either make the eye too strong or things that make the eye too long. So increased refractive power of the eye, what's going to make the eye too strong? Keratoconus that I showed you, lens changes, anterior dislocation like I showed you. Cataract can increase the refractive index of the lens, so you can get myopic shift for that reason. A diabetic person can, they absorb, when they're getting glucose in their lens, it's going to swell and become stronger. Kids with ROP tend to have larger anteriorly dislocated lenses, actually, so that's more axial. Excessive accommodation, people in accommodative spasm, like students who are studying too long and too hard, or if the examiner just isn't good at fogging the patient, you can get an increase in myopia. And then certain drugs, most notably Topamax is the drug that can cause swelling of the ciliary body, and then the lens iris diaphragm shifts forward, causes myopic shift, and ultimately angle closure glaucoma. Then there are things that increase the axial length, and that would include posterior staphyloma, congenital glaucoma, like I showed you, and also if a patient has a scleral buckle, that buckle it buckles the eye, and it squeezes the eye and makes the eye longer. And it's about 3 diopters of added myopia per millimeter of axial elongation. So it's not uncommon. I had a patient who had 6 diopters of myopia in one eye after he had a scleral buckle, and he also had strabismus, but this is a case where I did ask where the patient wanted the buckle taken out, and the retina surgeon was okay with it, so took the buckle out, but the myopic shift only went down by like a diopter or so it didn't change it that much. But that's because when I went in to do the strabismus surgery, even though the buckle was gone, there was this band of fibrosis that had been around the buckle that was still working like a buckle to hold the eye longer. So here's a patient who has had a hyperopic shift, and we don't know why. But when we look in the retina, we notice there's choroidal folds, and we say, gee, hyperopic shift and choroidal folds. That's suggesting something's making the eye shorter. So we get an imaging study and we see that there's a tumor behind the eye pushing the eye forward. So things that can cause hyperopia include, so here's another patient who comes in, vision's a little bit blurry, and it turns out that they need like another plus 150. And now it goes from, very blurry to still like 20/25, not quite their normal 20/20. And that patient has central serous retinopathy. So there's a little bit of subretinal fluid pushing the retina forward just enough to cause a diopter and a half or so of hyperopia. So that's a couple of examples. What are the other things that cause hyperopia? It's going to be things that make the eye too weak or make the eye shorter or effectively shorter. So what's going to make the eye too weak? Aphakia, obviously, or anything that can shift the lens posteriorly in the eye will move it closer to the retina so it has less effective plus power. Things that can interfere with accommodation can do that. And it doesn't take much. Patients who have a little bit of latent hyperopia and then if they lose that accommodation, even a half diopter of latent hyperopia, if they can't accommodate to overcome that, they're really unhappy with the blur that can take place. And then some drugs can do that. Marijuana, benzodiazepines, the ones that are listed here, can interfere with accommodation. And then what's going to make the eye short or effectively shorter? Tumor, like I showed you, central serous retinopathy. So what about this patient who has had an increase in astigmatism since the last visit? So this one, here's this pterygium, and it's sort of just like the foot, like I told you, it's just pushing on the side of the eye. It's warping the cornea and probably making it steeper in this meridian, unless it's pulling on the cornea, and that would be making it flatter in this meridian. Here's a patient who had a multi-diopter increase in their astigmatism, and you see here that they have Terrien's degeneration of their superior cornea. It's just like a relaxing incision that's going to get flatter in that meridian. And then here's a patient who's had some lens changes, this posterior lenticonus, and so we're getting lenticular astigmatism induced in this case. So what are all the causes of acquired astigmatism? So there's corneal causes, and that would include, progressive wouldn't be simple, but anything pushing on the eye, a chalazion, so a tumor, ptosis, and sometimes kids with ptosis or kids especially with hemangiomas, we've seen 7-8 diopters of cylinder just from little bitty hemangiomas that are positioned just right on the eyelid to warp the cornea. And then structural anomalies, keratoconus, I showed you earlier, Terrien's, pellucid marginal degeneration. And then lenticular causes of astigmatism would include lenticonus, like I showed you, or peripheral dislocation of the lens. So trauma that causes, or zonules breaking, or Marfan's with the lenticular dislocation. Now you've got like a steep meridian close to the edge, one side, but then you got the flat meridian on the other part of the lens. Notice that I do not have any retinal causes of astigmatism, because if the retina warps or tilts, it doesn't cause astigmatism. It causes metamorphopsia, distortion, like bad things, but unfortunately not something you can correct with an astigmatic lens. Lens coloboma is another one. And finally, this is a good one. Patient comes into your office. You've noticed 2 diopters. You just refracted her like a year ago, and now there's 2 diopters of astigmatism at an oblique axis. You correct it, you get the vision back, but you're like, where did that 2 diopters of astigmatism come from? So you do your Ks, and it's like the keratometry's there's no corneal astigmatism. So then you remember this lecture, and you say, I'm going to look for something going on that's pushing on the lens. So you transilluminate, and you get a little shadow, and you get the ultrasound and discover the ciliary tumor that's warping the lens and pushing the eye over. Pushing the lens over, causing astigmatism. So there, we made it through astigmatism. So let's talk next about contact lenses and sort of the clinical evaluation. And then these do come up they do tend to come up on board exams. So there's certain basics that we need to understand about them when we're thinking about contact lenses. So first of all is there are ways to figure out what the power of a contact lens should be when you know the glasses prescription. And so what I'm showing here in this diagram is that when a contact lens is properly fit, you're going to have some tears between the cornea and the back of the lens. You sort of need, this is a rigid lens. You need those tears so that when you blink, it can bring oxygen into the front part of the cornea, and it also provides some comfort so that you don't just have a lens suction down onto the corneal epithelium. So for that reason, we need to choose a base curve. We know the keratometry readings. We want to choose a base curve that's a half diopter steeper than the K values. And then we have to convert our refraction to minus cylinder format, which I'll explain why, and zero vertex distance, which we've already done. And then, but then what's the power that's ground in onto this rigid gas permeable lens has to be, you have to subtract that half diopter tear lens from the part that's vaulting over the cornea. So let's do an example. I think it makes it easier to remember. So a patient comes into your office, they want to wear rigid gas permeable lenses. Their refraction is plus 11.5 plus 1.00 times 35. Their K readings are 44.25 and 45.87. You don't have any trial lenses, but they really want you to prescribe them contacts, so what rigid lenses do you give? Step one is we choose a base curve that's 0.5 diopters steeper than the flatter K. So why is it steeper than the flatter K? Well, so if one part of the cornea is flatter and one part steeper, you want that disc of the contact lens to be just a half diopter over the flatter part, because the steeper part, say that's in front, say this is a contact lens, and side to side is the flatter cornea, and then front and back is the steeper cornea. Well, the steeper cornea is just going to kind of fall away more, and tears will fill that in. But this is the part, the flatter part's the part you want to fit, because that's where you get your minimum 0.5 diopter lens thing. So 0.5 steeper than the lower K, so that means your base curve is going to be 44.75 diopters, which converts to a certain radius, but I think in hard lenses we use these numbers. So then we need to convert our refraction to minus cylinder form. So new sphere is the old sphere plus the old cylinder, 11.5 plus 1 is 12.5. New cylinder is the old, same as the old cylinder with opposite sign. New axis is 9 degrees away from the old axis. But then we throw away the minus cylinder. Just drop it. And I'll explain why that works. So now our new lens power should be 12.5, right? Well, no, we have that 13 millimeter vertex distance, so now we got to convert that to zero vertex distance, so reciprocal of 12.5. That gives us a number. We subtract 13 millimeters from that number. Then we get the reciprocal of the new number, and that gives us 15 diopters. So it's a 15 diopter lens we give, right? No, because that half a diopter vault over the cornea left a tear lens behind it, and so we have to grind in 14.5 diopters onto the front of the lens with this particular base curve for this particular patient to correct the refractive error. So why is it that we throw away that minus cylinder? Well, let's look at, we'll see it here. So when you want to look at the fit of the contact lens, you can put in a drop of fluorescein because the rigid gas permeables don't take it up. And what you see is just a little bit of fluorescein here, but no touch. But see here, the cornea, surface of the cornea is touching the lens, so that's not good. You have pooling of fluorescein above it, but it's touching here. They're not going to be comfortable with those lenses. Here's what happens with an astigmatic cornea. You see how the fluid has come in to fill the bottom and the top, and that's your minus cylinder lens. So the tears under the contact are providing the minus cylinder correction. That's why you can throw it away when you're doing your calculations. This image of the fit of a contact lens looks rather like the Batman signal, so we call it the Batman sign. So that's hard lenses. How do you evaluate the fit of a soft contact lens? Because you can't put in the drop of fluorescein because you'll stain the lens, which I've done, but that it comes out with hydrogen peroxide if you have any handy, just in case that ever happens to any of you. So soft lens, you don't need the fluorescein. You just evaluate the movement under the slit lamp. So sit the patient at the slit lamp, have them blink, and watch and see if the how the lens moves. If it moves too much, then it's too flat. It's just like you might as well have just put a little piece of saran wrap in the eye or something. It's moving all over the place. If it's too tight, then it's going to suction cup onto the eye and not move at all when the patient blinks, and that's going to be uncomfortable too. So what do we do if it's too tight or too steep? We can change two things. We can either change the diameter or we can change the radius of curvature. So I have some drawings to explain why either of those is going to change the fit. And I feel a little bad seeing everybody take notes because you have the notes, they're emailed, and if you weren't emailed, you'll get them. But I know if you don't happen to have them in front of you, some people are. But anyway, just remember that everything here is in notes that you will have physically. So if we want to change the fit, we can change the diameter. So here's a contact lens viewed from the side, cut in half, and that has a certain curvature and a certain diameter. So if we increase, here's a larger diameter and here's a smaller diameter. So you see that when the diameter gets smaller, the lens just becomes flatter until if you have an infinitely small diameter, you're just going to have a perfectly flat lens. Whereas if we were to keep this diameter going more and more, we'll end up with a semicircle there that's very steep. So smaller diameter makes for flatter lens. Okay? So what about changing the radius of curvature? So here's a circle with a certain radius, and here's a circle with a smaller radius, and you see that the smaller radius is the steeper circle. So for the same diameter, if we cut the lens out of that, for the same diameter, the shorter radius is the steeper lens, the longer radius of curvature is the flatter lens. So a patient comes into your office and you fitted them with contact lenses and they went home with them, but they come back a week later saying these contact lenses are very uncomfortable, doctor. I can see fine, but they bother me a lot. What do you do? Well, I would have them sit in the slit lamp and have them blink and evaluate the fit. Okay, so you do that, have them blink, what do you see? Well, when I have them blink, I see that there's excessive movement of the lens. It's moving too much. So what does that mean? That means the lens is too flat. So what are you going to do about that? You're going to either choose a lens that has a bigger diameter to steepen it, or you're going to decrease the radius of curvature. So we're not going to go through that one. But again, this was in the handout. These are just, let's do this one though. So an eye has Ks of 42.75/45.87 at 80. So that's in the 80 degree, 45.7, in the 80 degree meridian with a spectral correction of this. What type of contact lens should be selected? A spherical soft lens, a rigid gas permeable lens, a toric soft lens, a front toric rigid gas permeable lens. So you see, what we have here is we have 2 diopters of astigmatism, right? Because 42.75 plus 2 is 44.75. It's 3 diopters of cylinder. We have Ks that have 3 diopters of cylinder. So this is what I talked about before. But you don't have any cylinder in the spectacle correction. So that has to mean that in addition to the 3 diopters of cylinder in the 80 degree meridian, that the lens of the eye must have 3 diopters of complementary cylinder in the 170 degree meridian that's balancing those out. So if you choose a rigid gas permeable lens, you're going to take away the corneal cylinder and unmask the astigmatism. Same goes with a toric. You don't need a toric soft lens because they don't need the astigmatic correction. That's just some fancy words to get you to confuse you. So this patient needs a spherical soft lens. So refraction got a lot more interesting when we changed it from prescribing glasses to doing surgeries. to try to fix refractive error. And so here, there are other courses that talk about the nuances of refractive surgery. Here, we just want to talk about some of the optical principles behind it. First being that all we're doing here is basically using a lathe to carve a minus lens into the cornea to remove some of to make the cornea less steep for this myopic person, an optical lathe, if you will. So, so we'll talk about the cornea, a little bit about radial and astigmatic keratotomy as well. So the radial keratotomy, what happened is these radial relaxing incisions would destabilize the periphery of the cornea so that the periphery of the cornea would steepen. So then what happens to the center? You're going to get compensatory flattening of the center. And so by by weakening and destabilizing the periphery, the center of the cornea flattens. So now the eye is no longer too strong. The astigmatic keratotomy is just like what we talked about. Again, you're just destabilizing, say, over here. So if the eye was too steep horizontally here, the cornea was too steep horizontally, by making cut here and here, you destabilize the periphery, and that flattens the center. So, I was here when Roger Steiner and Carmen Puliafito were here, and they were just playing. I was resident. They were sort of working with the laser that they were playing with, and talk about a paradigm shift. That the thought was, well, we could use the laser to make these radial incisions in the cornea, so we could do radial keratotomy with a laser, and so it sort of took that. And we were all stuck, the world was sort of stuck in that idea. So it just took that, like, stepping away from it and say, wait a minute, if you can cut the cornea, why not, instead of just cutting the cornea, like, etch the whole surface of the cornea instead and do your refractive surgery that way. And so thus was born PRK and then LASIK and other methods to follow. Again, you're just sort of etching a lens into the surface of the cornea. And then, but now with the femtosecond laser, we don't even, there's another way to do it, which is to basically to carve a lens. So carve a lens out of the middle of the cornea without having to even lift up a flap. So there's the little lenticle that we've carved out of the cornea, and now you use your little femtosecond laser to make an opening in the side, and then you just pull that little plus lens out of the cornea in order to correct the myopic refractive error. So this has some limitations, but certainly an elegant approach and a long way from using a laser to do RK incisions. It's also possible to treat hyperopia in different ways, including customized ablations with the laser, but also you can burn the cornea in the periphery. That's conductive keratoplasty. And if you burn it in the periphery, then you're shrinking this tissue. And so again, it's like you're stepping on, it's like you're pushing on the sides of the cornea so that you're getting compensatory steepening in the middle of the cornea to correct hyperopia. So again, you have other classes other places to learn about doing that. But what I want to talk about a little bit is the aberrations that can result from refractive surgery. And there's been lately more backlash, and let's hear what Dr. Oz has to say about it.
It's the world's most popular elective surgery, LASIK. It promises your eyesight will go from this to this. But what if LASIK could cause your eyes to see this, or even this? When I heard how life-altering these side effects could be, I needed to know why. So I sent investigative reporter Elizabeth Leamy to go undercover to find out.
And I'm going to take you there, not undercover. So a lot of this, now some of this has to do with the dry eye, but many of it has to do with the aberrations. And one of the aberrations, we'll just back up here for a second, is with the radial keratotomy, these little cuts created little points for diffraction to take place, for light to sort of get diffracted around these little apertures. And so there was so that was one issue, is diffraction. So we just sort of go back to some of the basics. So diffraction can create these little starburst patterns, but then if you get an irregular ablation or a hazy flap surface, then you can get a lot of scattering of light. So this shows up, again, we're getting the scatter this way, but you can get it in the opposite direction too. And then when you have these irregular ablations and you have a lot of scattering, you also get a reduction in contrast sensitivity. So patients can say that they have a much harder time seeing on a cloudy day, driving on a rainy day, because of their reduction in contrast sensitivity. And then the patients who find their way to me may also be victims of multifocality, where, for example, here there's a little island that was left behind in a astigmatic keratotomy, or decentered ablations can also create, you basically have two different refractive surfaces within the pupil, and so those two different refractive surfaces within the pupil can end up focusing the light into slightly different places on the retina, so you can get monocular diplopia, triplopia, multiplopia, both bilateral monocular diplopia. And then you can also have coma, which is again decentered ablation. So you get this fringing or distortion of images through this particular type of aberration. And then spherical aberration. Our corneas actually have spherical aberration, and our lenses have spherical aberration too, but the two are complementary, and so they tend to work it out between themselves so that the eye itself has pretty minimal spherical aberration. So if you just do a plain spherical ablation, you can end up inducing spherical aberration, and that causes halos around objects. And it's sort of, there's in this one that I cite here, this AAO summary, Munnerlin, he goes through very nicely, and really, I'll say one thing causes one and one causes another, but the decentration can cause some monocular diplopia, but it can also cause some halos and the scatter. So all these different imperfections cause somewhat of all of it, but these are sort of the main aspects of the complications that you can get, optically speaking. Not to mention the patient I saw the other day who used to be a myopic anisometrope, and he ended up with as a hyperopic anisometrope the opposite way, and his accommodative effort to try to overcome just a half a diopter of hyperopia from having been a -6 to a +0.5 on the right eye caused him to become esotropic and have double vision. And so the only way to treat his esotropia was to put him in contact lenses to make him myopic again. So all that said, for all these complications, at the same time, we have the power now with LASIK to do these customized ablations where we not only do the spherical part and the cylindrical part, but also look for these irregularities and potentially ablate the irregularities out of the system and give people better vision than they could have with glasses. So the potential is there to do customized ablations that give us better than even glasses can get us. If we can do it right. So that's refractive surgery. And then the ultimate refractive surgery is intraocular lens implantation. And we'll talk a little bit about the formulas that we use to calculate those things. So there are the empirical formulas are the SRK and the SRK2, and then theoretical formulas we'll talk about a little bit. So here's the SRK formula. By empirical, that means that Saunders, Retzoff, and Kraft, SR&K, did thousands of cataract surgeries, measured their axial length and their keratometry prior to surgery, after surgery, and then determined what the numbers were and how to predict the outcome of refraction. And they ended up also with a this number, the A constant, which varies for different intraocular lenses and has to do sort of with where that lens sits within the eye. But anyway, they came up with a really a very good way of predicting IOL power in about accurate in about 95% of patients, or at least 90%. And then when you modify that, but then as you get into the extremes of axial length, long and short eyes, then it's no longer a line, it's a curve. So they modified it a little bit with the SRK2 to modify it for long and short eyes. But still, that's maybe 97% or so, or 95% who get it. But there's still 5% who can end up with fairly significant errors in their refraction. So, we'll just skip that. Whoops, sorry about that. So then the theoretical formulas came in, and the theoretical formulas go back to that schematic eye. And the key for all the early theoretical formulas weren't very good, but the SRKT, the Holiday, they're very good at predicting exactly where the lens ends up in the eye. And that's the key to the success of any of the theoretical formulas, is to know exactly where that lens is going to be, because you've got a 20 diopter lens in there, shifting at a fraction of a millimeter one way or another, you're going to get big shifts in power. So if you just put the lens in, like if you have a vaulted lens, some of the 3-piece lenses are vaulted. If you put it in backwards, then you end up, instead of it being vaulted backwards, it's vaulted forwards. So you can get a big error that way. But anyway, the theoretical formulas are very good at putting those numbers together, predicting where the lens will end up in the eye, and giving you a good number. So that gets us through refraction from all the way from visual acuity testing all the way to refractive surgery and intraocular lenses. And what we're going to do next is move into magnification and telescopes. So it's 11:12 Boston time. For those of you who are here in the Meltzer Auditorium in the Massachusetts Eye and Ear Infirmary, a short throw from the Charles River in Boston, we'll be having lunch brought in. We'll just do it a sort of a quick, get some lunch. It'll be like a whole, say, 20-minute break for you to get lunch and get fed. But rather than keep you here all afternoon long, I like to just concentrate the lunch and just keep moving right along. So we're going to talk next about magnification, low vision, mirrors, and prisms. And then still working our way towards optics in the office. Make sure you can see my arrow. Yep. All right, good. So magnification. So we'll talk about the different types of magnification, and then we'll go into telescopes, magnifiers, and sort of how they work and how we can calculate what they do. And then finally, anisoconia and how that relates to our patients. So magnification can be transverse, axial, and angular. And the first two, transverse and axial, have to bring us back to our U plus D equals V. And then angular is when we're talking about hand magnifiers, telescopes, that sort of thing. So transverse magnification, here's our object, our extra-axial extension, our central ray, our image. So, and remember how I said with the central ray, we can also figure out how magnified it is. So magnification is just how tall is that image compared to the object, right? Because if the image is twice as high as the object, then it's a 2 times transverse magnification. But the problem is we don't know how high that image is or how tall it is. But what we do know is how far away the image is, and we know how far away the object is. And by, remember, similar triangles, if we know the ratio of the distances, then we know the ratio of the heights. And so image height over object height is the same as image distance over object distance. So all we have to know is image distance over object distance, and that gives us our magnification. Now, if you look in books, a lot of times they'll have like we have our big U and our big V, so they'll have like a cursive U and a cursive V, and that's just the reciprocal of U and V. But I found that I was just getting confused about who was which, and so I just keep falling back to image distance over object distance. But if you're smarter than that, which most of you are, you can just remember to carry those reciprocals with you and divide them out that way. So now, when we're looking at magnification in the eye, then the central ray passes through the nodal point, and so again, image distance here is going to be 17 millimeters, and an object distance is whatever. So magnification, but we can't use magnification in the eye to, like, if you want to know how strong binoculars are, that's not going to work because the objects and the images, they're off at infinity, so you can't just do image distance over object distance. But this will tell you, like, if you want to know the magnification when you're looking at something inside of the eye through a 20 diopter lens, and we'll get to that later. So that's transverse magnification, and we're not going to take the time to go through this, but we can do that in the U plus D equals V. You can also do the magnification of these by doing image distance over object distance, but it's a kind of a flog to go through that. So we won't do that for now. Now, axial magnification is magnification along the axis, and it's always the square of transverse magnification. So here, let's say this image is twice the height of the object. So the transverse magnification then is 2x, then that means the axial magnification is going to be 4x. So if it's twice as high, it's going to be 4 times as long. So this can cause distortion when we have 3D images and we're trying to, that is, like if you're looking in the retina at objects that have been magnified, then they may appear to be either flatter or taller than they appear to be. And again, we'll get to that axial magnification a little bit later. But in terms of just doing the calculations, it's just the square. Axial magnification is the square of the transverse magnification. So that's less important and relevant than angular magnification. So as I say, angular magnification is what we see when we're viewing objects either off at infinity, or we want to know how much magnification there is when we're using a hand magnifier. And the problem, again, with trying to do it with respect to the 17 millimeters from the in the back of the eye is that every eye is a little bit different. Not every eye has the same axial length, and so you end up with inaccurate calculations. What we want to know instead is, if I'm looking at the moon with my naked eye, and now I look at it instead, it's going to take up, say, 1 degree of my visual field. And if I look at the moon with my eyes, say it takes up 1 degree of my visual field. If I now look at it through a telescope, it might take up 5 degrees of my visual field. So that means that we've had 5 times angular magnification. And so that's doesn't matter what my what my refractive area is. It's independent of that. And so how do we calculate that? Well, when we're looking at, first we want to know when we're looking with a hand magnifier, so we'll get to a telescope. But it's the same idea. If I'm looking at something on the desk here with my naked eye, say I'm looking at a penny and it takes up 1 degree of my visual field, if I now look at it through a hand magnifier, then now it takes up, say, 4 degrees of my visual field. So it's going to be a 4 times 4x hand magnifier. But the problem is, with hand magnifiers, that's different than looking at things at distances. When I take it away, yeah, now it takes up 1 degree in my visual field, but if I'm this far away, well, now it takes up 4 degrees of my visual field, and so then, then the magnification, it's not relevant. So what we have to do when we're looking at hand magnifiers is to set a reference distance. That's how big of an angle does it take up. I'm waiting for that name to show up. Oh, somebody's not muted. So how much of it does it of the visual field does it take up at the specified reference distance? So to calculate that, we can calculate this theta angle f point centimeter, and we calculate and compare it to the reference angle tangent here, but the magnification ends up being d over 4. So it's the power of the lens in diopters divided by 4 gives you the magnification of a simple magnifier. So that also happens to be d times the reference distance in meters, because there's our reference distance, 25 centimeters. So that's the kind of the universally agreed upon reference distance for a hand magnifier as we compare it to 25 centimeter distance. So d over 4. And for those of you who are in advanced class, every now and then someone will set the reference distance at 40 centimeters instead, and then the magnification would be d times would be 40 centimeters over f, or d times 0.4. But for the rest of us, d over 4 is all we have to remember. So what that means, let's do an example before we get lost. So when we're looking at a patient's eye through a direct ophthalmoscope, if the patient is emmetropic and the examiner is emmetropic, the knob you have on the direct ophthalmoscope is 0. You're just using the 60 diopter power of the front of the patient's eye as a simple magnifier in order to look at the retina. And so the power of the magnifier that you're looking through then is d over 4 or 60 over 4 or 15x. So that means that when you look at the optic nerve through a direct ophthalmoscope, it's 15 times larger than it would look if you were to take the optic nerve out of the back of the eye and look at it with your naked eye from a distance of 25 centimeters. So that is, so anyway, that's the power of a simple hand magnifier. Now, I have this video here, and here, this is where somebody really was able to impress his friends and enemies alike with his coolness because of just how much he knows about optics. This is a Heineken commercial, and to set this up is that the whole ship is about, there's a big soccer match and everybody's excited, but they're on a ship that's about to depart, and they just have this tiny little TV to be able to watch the soccer match, so everybody's upset. So he's going to use one of the portholes of the ship as a simple magnifier. That's the tournament.
Okay, perfect.
There goes, up in the capstan. There's the porthole. Now we're getting ready for some nice globe on, so everybody knows he knows optics. Put it at the proper distance. Voila. Or optics in action. So let's go back and look at this in more detail. So here's the television that they all want to watch, and I calculated this, that it's 0.75 degrees of visual field that it takes up. But then once we get the lens at so this lens is going to be at the focal length of the television is going to be at the focal point of the lens, so the parallel rays are coming out, and at that point, when you measure this, it's 2 degrees of the visual field. So he was able to get a 2.6x angular magnification out of this as his hand or arm magnifier. So then there are telescopes. So what a telescope is it's like an optical lever that enlarges the image. So the idea here is you have something that's off at infinity, and so there are parallel rays of light coming into the lens, and then the rays of light are going to be converged to an image, but then they continue on and they continue to then diverge again. So what you do with that is you take a second, and you can think of it as going straight, but here we're showing it at an angle just to make it look more like a telescope, is you can take a second plus lens, capture these re-diverging images, and make them back into parallel rays of light. And if the two lenses have the same power, you'd have no magnification. But if the two lenses have different powers, then you create this magnification. Like I say, it's like a lever where it's the focal length of the eyepiece of the objective lens divided by the focal length of the eyepiece. But since the focal length is a reciprocal of the power in diopters, then the magnification of a telescope is the power of the eyepiece over the power of the objective. D eyepiece over D objective. So this is an astronomical or Keplerian telescope. And notice that we can trace the rays through here. So you see that the upper ray ends up on the bottom and the lower ray ends up on the top. And so that means that the object is going to be the image is going to be inverted with this kind of a telescope. And furthermore, the length of the telescope is going to be the sum of the focal length of the two lenses. So Galileo had a better idea, and here's one of Galileo's telescopes. He said, well, let's start with the same thing. We've got our objective lens. We have parallel rays of light coming in. It's going to converge the rays down to a point. But instead of waiting for the intermediate image to form and getting them again over here, let's interrupt that with a minus lens as the eyepiece instead of a plus lens as the eyepiece before they fully converge and convert them back to parallel rays of light. And it turns out that you end up with the same ratio of focal lengths just off to a virtual image somewhere over here. And so the magnification is exactly the same. It's the power of the eyepiece divided by the power of the objective for a Galilean telescope. But the difference is, if we follow this lower line, the lower line stays on the bottom, the upper line stays on the top, and so a Galilean telescope, the image is upright and not inverted. And furthermore, the length of the telescope is shorter because instead of adding the two focal lengths, it's the difference between the two focal lengths that gives you the length of your telescope. So the Galilean telescope is shorter and it has an upright image. So you can build much less expensive surgical loops, because surgical loops are just telescopes, but then you put a little ad on the front of them so that the rays of light coming from up close are parallel before they go into the telescope. So imagine a little ad up here to set your working distance. So surgical loops are just telescopes, and you can make a surgical loop less expensively, make it more compact, and have an upright image by using a Galilean telescope. Now, there are astronomical telescope loops too. Those are the ones that have really long, they tend to be much longer and heavier because they have to have inverting prisms inside of them so that the weight is from the inverting prism and the length is because they just have to be longer because you're adding the focal lengths instead of subtracting them. There are some advantages in terms of the quality of the image, so that's why, so I use astronomical telescope loops because of the quality image and the field of view is a little bit better. So you need to be able to calculate this, the magnification of the following lens combinations. A plus 20 lens, use a simple magnifier. D over 4, 20 over 4 equals 5x. How about and that's assuming a reference distance of 25 centimeters, the standard reference distance. How about a minus 20 plus 4 telescope? Well, that's a Galilean telescope. You put the minus 20 next to your eye. You hold the plus 4 out here. And so it's 20 over 4 is 5x when the minus 20 lens is the eyepiece. Now, if you flip it around backwards, it would be a 1/5 x telescope or miniscope. It would shrink everything down to 1/5 the normal size. What about a plus 20 plus 5 telescope? That's an astronomical telescope, so that's going to be 20 over 5 or 4x, but it's going to be a much longer telescope. We didn't calculate how long these telescopes are, but this is going to be the shorter one. And it's easy enough to tell us to calculate. Actually, why don't we do one, because since I didn't calculate, I'll calculate it for you now. This is question 6 in your pretest, and it says a telescope is constructed using a +20 lens as the eyepiece and a -40 lens as the objective. The telescope, so it either has a power of 2x or 0.5x, and the lenses are separated either by 2.5 or 7.5 centimeters. So I have to figure out two things to get out of this. So first of all, it's 20 and 40, and so the magnification should be power of the eyepiece over power of the objective. Now notice we put a trick in here. It says the +20 is the eyepiece and the 40 is the objective. So we have the +20 next to our eye and the 40 out here. So that's 20 over 40, or 0.5x. So it's a 0.5x telescope. And then the separation is 1 divided by 20 is the focal length of one, and 1 divided by 40 is the focal length of the other. So 1 over 20 is 5 centimeters, 1 over 40 is 2.5 centimeters, but since it's a Galilean telescope, then we're going to get the difference between those two, and so that's why we get 2.5 centimeters in length. So that's question number 6 out of our top 10. Now, when we correct aphakia, we get additional magnification as well. And it's because if you think about it, when you correct aphakia with an intraocular lens, you're putting the power right back where it belongs, so you're not going to get magnification there. But we could simulate aphakia by putting a minus lens inside of the eye, right? Because the power of the lens itself is about a 15 or so, or say it's a 18, 15. If I put a -15 IOL inside of a phakic eye, now we'd need some correction up front, but it would be more than +15 because you need more power as you get, because the vertex distance considerations. So you end up, anyway, I used to do the math on all this, but it's not necessary. It's just remember that spectacle correction, you're going to get like 25% enlargement of an aphakic refractive error, versus contact lens corrected, you're going to get 6% magnification, versus intraocular lens, you're going to get almost no magnification from correcting aphakia. Because it's like but the concept is it's like you're putting a little Galilean telescope inside the eye, because when you take out a plus lens, it's like putting a minus lens in. It's like putting in a -15 eyepiece. Even ordinary spectacle lenses do cause some magnification, as you all know from looking at strong glasses, and it's 2%, but the number is 2% per diopter of power at the standard 12 millimeter vertex distance. So plus lenses magnify, it's like a Galilean telescope. Minus lenses minify, it's like a reverse Galilean telescope. Because the minus lens, the eyepiece is going to be out here in front. And again, same concept of putting error inside the eye. So anisoconia is when there's an image difference between the eyes, and most people can tolerate a difference of 6 to 7%, which is, if it's 2% per diopter, that's the number I want you to remember, 2% per diopter. So it's 6 to 7%, that's 3 to 4 diopters. So for example, if the right lens, if you have a -3, so let's say a patient has cataract surgery and their correction's +1 bilateral before cataract surgery. No, let's say they're -3 bilaterally before cataract surgery, and then something goes a little wrong and they end up +1 in their right eye after cataract surgery. So what kind of magnification are they going to be subjected to? Well, they have 3 times 2, 3 diopters times 2% is 6% smaller in the right eye, and now they have this +1 lens on their left eye times 2% is 2% larger. So now instead of 0 anisoconia when they were -3 on both sides, now they have 8% anisoconia, so that may or may not be tolerable to the patient. This child has a lot more anisoconia than that, but kids are more tolerant of anisoconia, and if I had a patient who had 10 diopters of myopia in one eye, plano in the other, but was put in her glasses at a very early age, and she ended up with stereo, and with no anisoconia because her brain just developed to notice that. Now, I don't see that patient anymore, but I worry that one day she'll get cataract surgery and someone's going to make her plano in her right eye, in the -10 eye, and plano in the other eye, and now she's going to have, 10 times 2, like 20% to her brain, 20% anisoconia from having lost her anisometropia. So how do you fix this? Let's say this patient was symptomatic. The simplest way to think about fixing it would be you put a plus, not a +1 contact, but put a +4 contact on the left lens. You put a +4 contact on the left lens, now they're going to need -3 glasses to fix it. And so now you're down to 0. Now both eyes have -3, so now you're down to 0 anisoconia. Now you don't have to go that far, right? Because people can tolerate 6% difference. So a +1 contact lens would probably be fine, but it would just still leave some anisoconia behind. So speaking of magnification brings us to thinking about low vision and how do we correct low vision. And so we'll talk about a number of different topics. First, just for those of you who are in the United States, actually, it got awfully quiet. I was just making sure that it's like when the kids get quiet, so you think there's something wrong. This is the federal definition is that the best corrected vision in the better eyes 2200 or worse, or the field of vision is 20 degrees or less. And that doesn't vary by state. That's a federal definition for with tax consequences. But every state has different requirements for driver's license. So we won't go into that. So when we are evaluating a patient with low vision, the first step is we want to get a good visual acuity. And if they can't see the big E on the eye chart, then it's hard to have any sort of a starting point. So one way, if they can't see the big E on the eye chart, is to there are these low vision cars that you can use to measure visual acuity. But of course, as we talked about earlier, you can also just move the patient halfway to the eye chart or a quarter way to the eye chart, as long as you keep track, and then just change your numerator. If you're 2 feet away, and if you were 20 feet away and you're 2 feet away, then it's instead of 200, it's 2 over 200, which is 20 over 2,000 visual acuity. Then, once you've quantified the vision, you have to find out from the patient what they most need, because a lot of these patients are either they're maybe elderly, they're not going to have hours to spend with you, or their kids, so you want to what's the main thing you need? And usually, most patients, what they need the most of low vision is they want to be able to read again and to function up close. And so there are a variety of near aids that we can talk about, that we can offer patients to be able to help see up close, and that includes plus lenses, loupes, electronic displays, and non-optical aids. So high plus lenses are the simplest way to go. You can put them in the reading glasses, or you can put it even in the bifocal, and you can prescribe, a 20 diopter bifocal. Those are available from special houses. The problem for those is that you see that the working distance is going to be the reciprocal of the power. So if she's wearing a plus 20 ad, then she's going to be 20 over 1 over 20, or just 5 centimeters away in order to be able to see clearly. And if you're binocular, as this person is, so this person's binocular and working 5 centimeters away, well, it's awfully hard to maintain convergence at 5 centimeters if you want to remain binocular. And so in those cases, you basically have a convergence insufficiency because you're always 5 centimeters away, so that's treated with base-in prism. So this would be not only plus 20 lenses, but also with base-in prism, so that the patient can maintain single vision. So high plus lenses have the advantage that both hands are free, so you're free to use both hands, and so your field of view is also wider. But you're locked into a certain distance away from the paper, and can be an uncomfortably close distance. So as an alternative, there are handheld magnifiers. And these also range from 5 to 20 diopters, which means 1.5x to 5x. And so you see the advantage here is you hold the hand magnifier at the focal length, and then it's parallel rays of light coming out, so you can move as close to or as far away from that as you want, and it stays in focus without any need to accommodate. So you can get good magnification. The disadvantage is that you have a more limited field of view, and the lighting can be problematic. And if you're unsteady, if you have a tremor or arthritis, it may be hard to hold the magnifier in place while you're trying to read. So there are stand magnifiers that do not require you to hold them in place, and this bubble one has a pretty good field of view. Still not as good as high plus lenses, but better. That can be used. But the lighting isn't always so good either. You see, that one has sort of some trouble getting the light in there. And so there are lighted magnifiers as well. It's like, oh, that one started moving. So the lighting can help. And here you see the compromise between, yes, you get more magnification with this one, but you also have a smaller field of view. So those two things have to be reconciled, and everyone's a little different in what they want. You can also get like a little reading line in there that some people can find helpful as well. So to summarize, the primary help that we have for patients with low vision are high plus lenses in glasses or handheld magnifiers. The high plus lenses leave both hands free and have a wide field of view. The handheld magnifiers allow a variable eye to lens distance. And so it's actually less distracting for many elderly folks to use a hand magnifier than to be holding things up very close when they're reading. So this is, you'll commonly see people using these hand magnifiers. Now, if that's not enough, if 20 diopters, isn't practical or effective, then there are loops, close focus telescopes that can be used. And here you see that this is allowing a longer distance from the person to the page. The field of view is somewhat more limited, but not as bad. But those of you who've used loops, it's not great. And also, those of you who've used loops know that you're kind of locked into one distance. Even though the distance is further away, if you get too close or too far, then you're going to go out of focus. And when you're looking through loops, the accommodative demand is the square of the accommodative demand when you're not looking through loops. People have asked me that, so that's loops, but they're not commonly used. The other thing is that most people don't want to be walking around wearing a contraption like that in the grocery store or when they're having, playing cards with friends. So we usually revert back to that. But then there are also closed-circuit television readers that people use. That requires a certain amount of dexterity, but they do have that advantage of being able to reverse contrast. So some people do okay with the CCTV readers, and then there are computer scanners. But really, it seems that the best low vision aid that we have nowadays is just going like this on the iPad. So this is the low vision aid of 2019. But still, you have to interact with phones. You have to so large print phones. And we can forget this as ophthalmologists or working because we're focused on the pathology, but large print books, signature guides, large cards, and then lighting is important to use. And I found this video. There's something about it. It's just
no more than a 60-watt bulb is needed to provide enough illumination.
It's like, does he know she's there?
The closer the light is, the brighter the illumination. It is also important to place the light below the eye level.
She's talking about
directed away
exactly
from the
how to
face
position the
to avoid
light, and
glare into
it
the
is
eyes.
important and helpful to
When using a
patients to get
magnifier
it just
with the
right.
the light must be placed.
So, so then there's trying to see things at a distance, and it's easier to find aids for up close. It's a little harder to find something to help with distance, and that generally involves having people wear telescopes of some kind, monocular telescopes, binocular, as you've shown here. These are little bioptics that are built into the glasses. And so what you do is you're walking around and you're getting your peripheral vision, because we're all 2400 peripherally. But then if you need to see a sign, then you can position yourself to sort of read that sign and then go about your business. There are some digital versions of this, virtual reality goggles that have magnification built into them that are out on the market. You know, over time, those perhaps will begin to grow in their acceptance. We also don't want to forget that some patients just do better with control of glare and having the proper sunglasses, or even keeping them partially dark adapted. Achromatopsia patients need like dark red glasses in order to be able to function, but will do very well with those. Macular degeneration, there's just a lot of, you don't need all that blue light bouncing around inside of your eyes, so patients with macular degeneration can do well. And then we like to do surgery, so are there any surgical options? Well, there is an implantable mini telescope that you can put in, and here's a video of one of those going in. So that has some promise, but practically speaking, I'm not sure that many people have taken this up, but it's at least there. I've also considered you could just leave a person aphakic and then give them high plus lenses. It seems to me that that's sort of a natural telescope. Take out their intraocular lens and put them in aphakic spectacles. You'll get magnifiers that way, but I don't think anybody wants to do that. So that's telescopes, magnification, low vision, all sort of wrapped into one. And now we're still in other optics of note. We have prisms still ahead, but let's talk about mirrors first. So we'll start with the laws of reflection and then go into plane, concave, convex, and then concave mirrors, and do our U plus D equals V for the mirrors, just as we do for lenses. So, because a mirror, it really is, you can think of it as a lens, but it's a lens that flips over the image space, so that, because it's reversing the direction of light. So a convex mirror is going to add minus vergence. A concave mirror is going to add plus vergence, and the plane mirror, like shown here, that doesn't change the vergence of light at all. So a plane mirror is just taking the light, so the light from the shoe down here, from the foot, it's going to come halfway up the mirror and then up to the person's eye. And so you see that for a full length, to see your whole self, you actually don't need the full length of a full length mirror. You only need about half. You actually need a little more than half, because if your foot protrudes in front of you, then in order to pick up your foot in front of you, you'll need a little bit lower on the mirror. But the basic concept is such. You see that the image is upright. The image is not magnified in a plane mirror. Different mirrors have different behaviors in terms of whether the image is upright or inverted, and whether it's magnified or minified. And so Dr. West took these pictures with different kinds of mirrors, close up and far away. This is a plane mirror. And so you see that no matter the distance, that the image is upright, and it is, and in addition, the magnification is the same, because the field of view doesn't change no matter how far away or how close up you are to the mirror. The field of view is completely unchanged. Let's contrast that with a concave mirror. A concave mirror, here she is far away. Now the image is inverted and minified compared to what we saw. Up close here, the image is clearly upright and clearly magnified. Here's a convex mirror. And so here you see that the image is upright. and that it's minified, and you know it's minified because it says right here, objects in mirror are closer than they appear, which means that they're smaller, I think, yes. So minified mirror, and then here is an astigmatic mirror, which happens to be an oil tanker, which is flat in the horizontal meridian but curved in the vertical meridian. So you've got minus. It's a convex mirror in the vertical meridian that's shrinking the image, and it's just a plane mirror in the horizontal mirror. So you can have an astigmatic mirror. And actually, I was talking about the device that we're developing. So it turns out we thought we could like fix some trouble we were having by putting an astigmatic mirror in there, and so I actually wrote a prescription for what we thought would fix it, and it was like -1.5 plus 3 at 90, and then we just gave it to the optical shop, and they made it, and we stuck it inside, we coated it and put it inside the thing, and it ended up fixing that particular problem. A little convex astigmatic mirror. That was a concave astigmatic mirror, but so. Vergence calculations. So we can do our whole U plus D equals V thing with these mirrors. So let's try to do one here. We got a plane mirror, and we have an object that's 25 centimeters away. And so we want to know where's the image and how far away is it. So we're 25 centimeters away. So that means we have diverging light. And what's the vergence where it enters the mirror? Take a reciprocal. 1/0.25 meters is for diopters. It's diverging light, so it's -4. A flat plane mirror adds no vergence, so U plus D equals V. -4 plus 0 is -4. Then the light bounces off, and it's diverging off to our left. So where's the point of intersection? It's nowhere to the left of the mirror, so we have to create imaginary extensions of the rays of light back to a point of intersection somewhere to the right of the mirror. How far away is it? Take a reciprocal. 1 divided by 4 diopters is 0.25 meters or 25 centimeters away. So just like I told you, the image is just as far behind the mirror as the object is in front of it. Let's contrast that with a concave mirror. But first, if the mirror has some curvature, we have to be able to figure out how curved is it. And so to do so, and then to calculate the power from that. So it turns out that the reflecting power of the mirror is the reciprocal of its focal length. And the thing you might not know is that the focal length is half of the radius of curvature. So here's our center of curvature of the mirror. So that's the radius of curvature. And so then the focal length is, the focal length is half the radius of curvature. So the focal point of this mirror is going to be half the radius of curvature of the mirror. And so 1 divided by half, the focal point is 1 divided by the radius of curvature divided by 2, which means 2 over r. So the reflecting power of a mirror is 2 over r. Now remember when I said the refracting power of a spherical surface is n prime minus n divided by r a long time ago? Well, in a mirror, there's no refractive surface to pass through. So if you make the n a 1 and the n prime a minus 1, then 1 minus -1 is 2. So it's really the same formula, n prime minus n over r, except that there's no difference in refractive index. One's 1 and one's -1. So that's our reflecting power of a mirror. So before I get you too lost, let's do an example. So we have but before we do an example, we have to remember where does the central ray go? Because remember we did a central ray through the center of the lens. So does the central ray go through the center of the mirror? No, it does not go through the center of the mirror. It goes through the center of curvature of the mirror. So the central ray goes to the center of curvature of the mirror. Remember the focal point of the mirror is going to be half of that distance. And actually, let's just back up for a second to the focal point here. So remember the focal point is where parallel rays of light are brought into focus. And so if you wanted to light the Olympic torch with a mirror, you could do so. You'd have parallel rays of light coming in from the sun, and they'd all be focused into this focal point. So if you put the Olympic torch right there on that focal point in a sunny day, it'll burst into flames. Similarly, if you want to build a searchlight and project light out into the world, or a flashlight, you would put your light bulb here at the focal point and have the curve there, because then the rays of light coming out of the light bulb will emerge parallel rays of light coming out from this concave mirror. So that's the primary and secondary focal point. This is the center of curvature, which is where you draw your central ray. And so again, any images are going to have to fall along this central ray. Depending where they end up depends on the power of the mirror and the location of the object. So that's where we want to do an example. Oh, but before we do the example, let's not forget about the convex mirror. So a convex mirror has a center of curvature behind, but again, you're going to have the central ray goes from the tip of the object through the center of curvature of the mirror. Now, since a convex mirror is always going to have the image behind, you see a convex mirror, it's always going to be smaller than the object. Whereas with a concave mirror, the image could be, remember when you're far away, the image is inverted and minified, but if you get close, if the object ends up being where the image is, then the image is going to be where the object is. So then you're going to have an upright and magnified image. So it just depends on where the object is, where the image is going to end up. Now, finally, as promised. So we have a 4-diopter shaving mirror, and a person wants to shave, and so we want to know what kind of where is the image for that person who's looking into their shaving mirror. They're 16.7 centimeters away. They're getting up close to shave. And so where is their image? So we need to take a reciprocal, but it's a 4-diopter shaving mirror. We also need to know where is the center of curvature of the mirror, because that's going to matter. So, but we'll get to that. So we got something to take a reciprocal of. We're going to take a reciprocal of this distance, 0.167 centimeters, 0.167 meters is, oh, I'm sorry, I do have this. The center of curvature is 50 centimeters away from because it's 2 over r, and 2 divided by 0.5 meters is 4-diopter shaving mirror. So a 4-diopter shaving mirror is going to have a center of curvature that's 50 centimeters away. And I have examples in the notes that you're going to hand out. There's examples in the book. So, I'm just going to walk you through one. If you pick up a third of it, that's good. And then you'll get the rest later. So 4-diopter shaving mirror, D equals 2 over R, 2 divided by 0.5 meters equals 4. So the center of curvature is 50 centimeters away. We already are told that the object is 16.7 centimeters away. 1 divided by 0.67 meters is -6 diopters. U plus D equals V. -6 plus 4 is -2. So the light bounces off the mirror and then it's diverging on its way back out. So where's the image? It's nowhere to the left of the mirror because those are diverging rays of light. So they must be somewhere to the right of the mirror. How far away is it? Take a reciprocal. 1 over 2 diopters is 0.5 meters or 50 centimeters behind the mirror. Now, is it inverted or is it upright? We have to draw our central ray. Does it go from the tip of the object through the center of the mirror? No, it goes from the tip of the object through the center of curvature of the mirror. And so therefore, the image is upright and it is virtual because it's on the opposite side of the rays that define it. So, we can also, and then the magnification is going to be the image distance divided by the object distance. So the image is 16.7 centimeters away. The image is 16.7 plus 50 away, and the object is 16.7 away. So we can calculate the exact amount of magnification. So that's your basic calculation for a shaving mirror. Now, as you move the object closer and further, some interesting things can happen. So here, for a convex mirror, the image is always virtual because it's always going to be diverging rays of light bouncing off of this convex surface. But for a concave mirror, if the object is in here close where it was, you saw that the image was virtual. But if you put the object in just the right spot, then you can end up with a real image coming out of a concave mirror. And you can play some optical tricks with that, as I will show you in this video. So we're going to see his secret. Light bulb down there, concave mirror. Is it just the right distance to create a real image of the light bulb in the fake socket? So now an example of a convex mirror is the cornea. We all know the cornea as a convex mirror. It's quite a steep mirror too. The radius of curvature is something like 7 or 8 millimeters. And so if it's an 8 millimeter radius of curvature, then what's the power? Well, the power is 2 over R, which is 2 over 0.008, which is 250 diopters. Now, wait a minute, some of you may be saying, you just told me this morning that the power of the cornea is 50-something diopters, or maybe 45, or I don't remember, but it was 50 or 45. But that was the refracting power of the cornea. That's the power that passes all the way through the cornea sees. But the 4% of light that bounces off of the cornea sees a power of reflecting power of 250 diopters, which is 2 over R. So if we have a 250 diopter convex mirror on the surface of our eye, then where would the image of the where the image of the corneal light reflex end up? So if we're holding a little hand light and we're 33 centimeters away from the eye, then we should be able to figure that out by doing our U plus D equals V. So the light is 33 centimeters away. So we're 1 divided by 0.33 meters is 3 diopters. It's diverging light coming out of some object. So U plus D equals V. Negative 3 plus negative 250 equals negative 253 diopters. So it's minus vergence, so that means the rays of light are diverging coming off of the cornea. So that means the image is somewhere behind the cornea. How far away is it? Take a reciprocal. 1 over 253 diopters is 0.004 meters or 4 millimeters away. So that corneal light reflex is 4 millimeters behind the cornea, which means it's just behind the iris. Right about there, because the iris is about 3 millimeters back. So the corneal light reflex is about 4 millimeters back. So when we're using the corneal light reflex to judge strabismus angle, you see, it's not so easy. It'd be easier if the corneal light reflex were on the surface, because then we could sort of follow the eye. But instead, it's like halfway back on this circle. So when the eye rotates, say, 20 degrees this way, well, the light reflex only rotates half the distance that the front of the cornea rotates. So it's just hard to judge alignment by looking at corneal light reflex because of how far behind the cornea it is. So that's mirrors. So now we move on to prisms, and we'll talk about calibrating, positioning, combining prisms, and we'll get to chromatic aberration. In the end, once we get to chromatic aberration, then you'll know we're almost ready for part 4. So remember how a long time ago we talked about how when light goes from low to high refractive index, it's bent towards the normal to the surface. So that's what happens here when you go to the first part of a prism coming in at an angle. The little dotted line is the normal to the interface, so we're bent towards the normal to the interface. So if you now have a piece of plastic instead of just like flat, if you have it at an angle like this, now the one that's leaving, it's going to go from high to low, refractive away from the normal to the interface as it goes from high to low. So it's going to be deflected away from the normal. So you see what happens is you go toward the normal in, away from the normal out, and you end up with a net change in the direction of light, which is what a prism does. It deflects the light in a different direction. And and you can sort of think of it, the light is bent towards the base. You can imagine the sort of the rays of light just draped over the base, or just bent toward the base, B and B, however you want to think of it. But it can get a little confusing when you start to think about where the images go, but we'll get to that in a second. So now it's bent toward the base, but when the light impinges on the prism, you get different amounts of deflection depending on this angle of incidence on the way in. So here, the angle of incidence is 1, here it's different, here it's different. And so these are both the same power prisms, but they're at different angles, and so they're deflecting the amount, the light behind it differently. I made a little video with our ducky. So let's see what happens when I rotate that prism. Oh yeah, so less power, less, more. So it looks like there is the position of minimum deviation. And that's where the prism is calibrated for, that spot right at the end there. That's the position of minimum deviation. Everything else is, it's get more power because the angle of incidence is different. So when we hold our prisms and measuring strabismus, we need to be aware of the fact that we could get false numbers by holding them in the wrong place. So that position of minimum deviation is where the angle in is equal to the angle out. And so for plastic prisms, which we use almost exclusively in the US in clinics, the best way to simulate that position of minimum deviation is just to keep the prism, the back of the prism, in the frontal plane. So here the eye is exotropic, and if the back of the prism is in the frontal plane, the light's going to get bent that way, so it's going to do like so. Now glass prisms, they're calibrated differently, but we won't go into that. As long as you're in the frontal plane, then you should be okay regardless of where the eye is pointing. For vertical prisms, same thing. Now, if you're measuring side gazes, like turning the head left or right, you still want to keep the prism in the imaginary frontal plane, because even though the nose might be over there, the target's still straight ahead. So it's not like when you turn the head to the side, you don't want to bring the prism over there. You still keeping the prism in the imaginary frontal plane, no matter where the head is, to keep it in that position of minimum deviation. So that's called the frontal plane position, which is what we want. I actually remember, like, when I first was working as a fellow, and the orthoptist was watching me measure a kid, and I had my hand just like this, and she just like grabbed my hand and moved the kid, in front of the kid, and the parent just grabbed my hand and moved it to make me put the prism in the frontal plane. So now, what happens if the deviation is so large that one prism isn't enough? Well, then we can just put two prisms up, right? Except what's going on here is that we put up two prisms, but you can't even see his eye. And the reason you can't see his eye is because there's total internal reflection. The light can't get from the eye to your eye because it's all being reflected internally inside of the prism. So you can't just stack prisms when you're combining them, and here's why. If we look at these two prisms and they're stacked, coming in, we're at the proper, for a glass prism, we're at the proper orientation. But if we zoom in on this interface, it comes out of prism A, and it's on the way into prism B at not the right angle of incidence. So prism B ends up having an artificial boost in its power. And so if you stack them like this, then you end up with a much more prism power than what you think. So instead, you have to hold the prisms in so here you can get total internal reflection. So you have to hold the prisms like this and keep them both in the position of minimum deviation. So like one thumb is here, one finger's here, one finger's there. You can sort of do it like that. Or if you're not so dexterous, then you can hold the two prisms over separate eyes and add them up that way. But of course, this wouldn't be it wouldn't be optics if we could just add 1 + 1 = 2. 50 + 25 does not equal 75 in the world of prism diopters. So let me explain why that is. We have to understand what a prism diopter is. So when you have a prism and the light's coming in, and it's going to deflect the light towards the base, right? Prism deflects light towards the base. And so if you're 100 centimeters away from a screen, say, which is 1 meter, but 100 centimeters, if the light moves 15 centimeters down, then it means you have a 15 prism diopter prism. That's the definition of a prism diopter. How many centimeters down does it move at a distance of 100 centimeters when you put the prism in place? And so that's all well and good for 15 centimeters. Let's say you have a stronger prism that bends the light at a 45-degree angle. Well, then at a 100 centimeter distance, it's going to go 100 centimeters down the screen. So that's a 100 prism diopter prism. What if you have a prism that can bend light at a 90-degree angle? Well, then you can go all the way down to infinity before the 90-degree angle bent light is ever going to make it to the screen. So 90-degree angle is infinite prism diopters. And so you see, as you get into these big prism numbers, it goes a little haywire. It's all well and good here where it's roughly 2 prism diopter, 1 degree equals 2 prism diopters. But once you get above about 60 degrees, then the numbers go off and they don't add up. So there are formulas and such, because if you're adding 2 prisms together and you're getting up in these higher numbers, then they're not quite linear. It's probably not that big. Most of the time we're not operating on much more than 100 prism diopters, so it's probably not, I doubt any patient has ever been harmed by not adding them correctly, but we like to do things correctly. So the next thing is, I've so far been talking about how light is deflected towards the base, right? But something else can happen when you're viewing prism through your eye. And let's look at this video to show you what I mean. So we're going to be looking at where this screen is, and I'm going to compare what it looks like when I put the prism base down in front of the projector versus base down in front of our own eyes. So when we put it in front of the projector, the image is deflected toward the base, like I said. Okay, that's all well and good. Let's put it in front of ourselves. Whoop! Now it goes toward the apex. So what's going on there? How can that be? Same prism. It's not doing anything tricky, but up it goes toward the apex. So obviously nothing as different is happening to the prism, but what happens here is that when you're viewing with the eye, the light is still bent towards the base, but we are creating imaginary extensions of the rays of light back to a point of intersection somewhere else. And so the image is a virtual image that's displaced towards the apex. So this is a real image on the wall. This is a virtual image that's displaced towards the apex. So if we have a patient, say this is an orthophoric patient, no problems, no complaints, and we now are going to introduce a base up prism in front of his right eye. So is that going to cause a right hypertropia or a right hypotropia when we put that base up prism up there? Well, when you look at the eye, sure, it looks like the eye is going down, so that must be a hypotropia, right? But it isn't. It's actually creating a hypertropia. And let me try to explain why that is. So first of all, you can kind of tell that it's a hypertropia because if you look at the corneal light reflex inside of the pupil, even though the whole virtual image of the orbit shifted down, you see how the corneal light reflex is low in the pupil, so that means the eye is a hypertropia. Another way to think through this is to say that, well, gee, I just gave the patient a base up prism, so to fix that, I'm going to need a base down prism. And I know from my clinical experience that a base down prism is going to correct a hypertropia. So you can sort of reason it through that way if you have enough clinical sense to know what a base down prism is correcting, which we sometimes will forget. So then the other way to think it through is to imagine that there's a little man with a laser pointer inside of each eye. And so they're both pointing at you. So the little man inside of this eye, his laser pointer is pointing right at you, and that's not going to change. And then in this circumstance, there's two little laser pointers, and they're pointing right at you. But now, with this base up prism, the little laser pointer light's going to be deflected towards the base, which is up. So that's a right hypertropia, because that's the visual axis. That little laser pointer light is the visual axis. It's deflected up this way. And so that patient has a right hypertropia. And so if you were to do a cover test here, you would measure a right hypertropia, you'd fix it with a base down prism. Now people can sometimes get confused when I do this explanation because they're imagining that the person's trying to fuse through this giant prism. And then they're thinking that the eye is coming down. So don't confuse yourself with that. Just think about what's happening to the pathways of light as they emerge from the fovea. One's going up when you have base up prism. It's just going to get deflected toward the base, and that's what happens to the visual axis. Now, we don't go putting prisms in front of people's eyes by accident, usually, but we can do that when we go putting lenses in front of people's eyes that are off-center, and that's because of Prentice's rule. And remember, when I went through the top 10, the number one on the top 10 list was Prentice's rule of all things. So I'll explain why we have that as number one. But and what Prentice's rule is that as you get away from the optical center of the lens, you have induced prism power, and the further you are away from the lens, the stronger the power exerted. And the formula is delta equals H times D. That's H, the displacement away from the center of the lens in centimeters. Remember, all day we've been telling you, been hammering it, convert to meters, convert to meters. But when it comes to prisms and Prentice's rules, it's in centimeters. Prisms are a centimeter sort of a thing. So H in centimeters times D, the power of the lens, in diopters. And as you look at this picture of the lens, you can sort of imagine that you're going to be getting prism power here because it kind of looks like a little prism there, when you're up here on top. And in fact, I developed a little visual mnemonic to help remember that. A plus lens looks like two prisms that are base to base. So when you're above the optical center, it's like base down prism. When you're below the optical center, it's like base up prism. And a minus lens acts like two prisms that are apex to base apex. So when you're above the optical center, it's like base up prism. And when you're below the optical center, it's like base down prism. And so when we look at people who are wearing glasses, we can see their prism power depending on if they're wearing plus or minus lenses. Here, he's wearing minus lenses because the virtual image of the side of the face is deflected toward the apex of the prism. So that must be prism's apex to apex, which must be minus lenses, whereas here, the virtual image of the side of the face is deflected towards outward, and so that must be prism's base to base, so that must be a plus lens, which you can tell anyway, because the minification versus the magnification, but we can also tell that way. This can also lead to trouble, as I say, when lenses get displaced, when optical centers get displaced, we can end up with induced prism that can be symptomatic and send patients to my clinic where I have to spend an hour trying to sort that out. This child has bent glasses, and this can cause a vertical strabismus, and we had a case very much like this where it was actually Dr. West who was paged by plastics to clear the eye before surgery because a kid had been hit in the eye and been hit in the head with a soccer ball and was seeing double, and so they were going to race him to the OR to treat his orbital blowout fracture, but they wanted ophthalmology to clear the patient first, and so it turned out that the glasses looked sort of like this, and the patient was seeing double, and Dr. West bent the glasses back into shape, put them back on the patient's head. The patient was now seeing single, and the surgery was canceled. So that is now there's one other thing that plus lenses can do, and that is they can change the amount of strabismus that you measure when you're preparing a patient for surgery. So what do plus lenses do? So plus lens, let's just draw the little map here. So let's say we have an exotropic patient who wears plus 10 lenses. We have 40 prism diopter XT. Well, you see that the patient, that this left eye is now going away from the optical center, so the patient's like they have base-in prism, which treats the XT, so you're going to measure less exotropia, and it's 10, let's see, I think maybe I took the formula away, but I don't think you have to know the formula, but it's about, I'm blanking on it, 20% for 10 diopters. It should be it's 20% here, I think. So it goes from 40 down to 30 prism diopters of exotropy. The important thing is to remember what it does, not how much it does. So we have a significant change in the measured XT. So you might operate for an XT of 30 when actually the patient had an XT of 40. So you're going to get a 10 prism diopter under correction. And the opposite is true for high myopia. Here's a minus 10 myope, and it's 2.5 times diopters. That's what 2.5 times the diopter. So that's 25% change. So you have a 40 prism diopter XT, but when measured through minus 10 lenses, it's going to be a 50 prism diopter XT. So you operate for 50 on this patient, and you end up with a 10 prism diopter overcorrection. So the mnemonic here is minus measures more. The measured deviation with minus lenses is greater than the true deviation, and the opposite is the case for plus lenses, which measure less. And the funny thing is that it's the exact opposite of what the lenses do to the cosmetic deviation. Here's a patient with high minus lenses and an ET, and you can barely tell he has an ET. When he takes the glasses off, you can tell. So the minus lenses decrease the cosmetic deviation, but he actually increased the measured deviation. Now, I think in practical world, in the real world, it may not be that relevant because the magnification makes it harder to see the endpoint of cover testing anyway. So I think the accuracy of the cover testing may be reduced here compared to when you can really see the glass as well. But party line is, multiple question answer is effective deviation is decreased by plus lenses and increased by minus lenses. But the cosmetic deviation, it's the opposite, is increased by plus lenses and decreased by minus lenses. So 2 ways to find solid ground in this topic. One is, from your intuition, plus lenses make the eyes look bigger, so they're going to make strabismus look worse. The other thing is minus measures more. So between those 2, you should have it. So then let's go through. Have they delivered any food out there yet? Yeah. Okay, great. So let's go through the number one question that people like to ask to show that you know your optics. And this is a patient who's seeing double after cataract surgery. So the patient had -3 prescription bilaterally, and they have cataract surgery. It didn't go so well because the post-op refraction in the left eye is +1 +3 times 90, and the patient says that, well, I can see okay at a distance, but I see double when I'm reading ever since the surgery. And I had a patient who was like this and who got a neurosurgical consultation because of the family connections. But in fact, what happened is they were seeing double in the reading position. So let's figure out why that is. So we'll break it down to the right eye and the left eye, and we'll separate them like so. So here's the right eye wearing -3 sphere. We're reading 1 centimeter below the optical center. So delta equals h times d. That's 1 centimeter times 3 diopters is 3 prism diopters of base down prism that we have in front of the right eye. Here's the left eye. We're 1 centimeter below, but how much power is in the vertical meridian? Uh-oh, we have to go back to our, got a cylindrical lens. Is it 1? Is it 3? Is it 4? Well, remember that little trick is if we draw a power cross, it's going to be +1 on the 90, it's going to be +4 on the 180, but we only care about the 90 because we're just going down. So it's +1. So it's 1 centimeter times 1 diopter is 1 prism diopters, but it's a plus lens, so we're below the optical center of a plus lens, so that's base up prism. Okay? So we've got base, 3 base down on the right, 1 base up on the left. Do they cancel out? Don't think so, because base down and base down would cancel out. Then you just have yoked prisms, but no strabismus. But 3 down on one side and 1 up on the other side, they add. So now you have 4 prism diopters of disparity between the two eyes. So it's as if you've introduced a 4 prism diopter base down prism in front of the right eye, or a 4 prism diopter base up prism in front of the left eye, either one. We'll say it's a 4 prism diopter base down prism over the right eye. So what kind of a deviation is that going to cause? Well, I've got the little drawing right here. Actually, I can do it here too. 4 base down, we got the laser pointer visual axis coming out of the eye. It's going to be deflected toward the base, so it's going to cause a right hypotropia or a left hypertropia when the patient is trying to read through these glasses. He's got a 4 prism diopter vertical deviation induced by this anisometropic correction. So what are you going to do about it? You give him, just grind in 4 prism diopters of prism into the glasses? Well, that'll help with reading, but now he's going to see double straight ahead where he was through the optical center, so that's not going to work. You could maybe grind in 2 and hope that he'll fuse 2 here and fuse 2 in reading position. That might work. Put him in contacts. You could lower the optical centers about halfway, and again hope that that's enough. But what we usually do is, or what we can do is we can give slab off prism. So that's a special form of grinding of a lens that puts the prism only in the reading position. So in this case, you would slab off 4 on the more minus lens to eliminate the double vision in down in reading position. And actually, we'd probably measure first and see, he's okay here. You measure 4, but then you try, and maybe the patient only needs 2 to fuse down there, so then you only have to slab 2 off, and that might make it easier. So it's a real thing. I've done it. I prescribed slab off prism 2 whole times in my life, and this is my specialty. So maybe you won't end up doing this very often, but why does this show up on tests so much? Well, you have to know about power crosses, how to figure out what's in the vertical meridian. You have to know how to execute Prentice's rule to figure out induced prism away from primary gaze. You have to figure out what kind of prism gets induced and whether or not they add up or subtract. You have to understand what kind of deviation is created when you introduce prism in front of the eye, and you have to understand how to correct such a deviation when it occurs. So you get 5 big knowledge points for the price of one 1-minute multiple choice question. I'm just saying. So let's, we still have more in the bifocals. I think I've starved you long enough. And we're only going till 2. So let's take, like I say, a 15, 20-minute break. So we're still talking about prisms, prism power. In this case, talking about, I wanted to talk about 2 things that can happen with bifocals related to prisms, and that's image jump and image displacement. And this is what happens when the eye transitions from looking through not bifocals to crossing into the bifocals, where you get image jump. and then to being all the way into the main part of the bifocals where you get image displacement. So image jump occurs when you get that sudden introduction of prismatic power at the top of a bifocal segment. And so the image jump depends exclusively on the design of the bifocals. Different bifocals will cause different types. So the round top bifocals, which we don't see very often, the edge of the bifocal is very far from the optical center, so you'll end up with a lot of image jump. The flat top segments, you're close to the optical center of the lens, so you get minimal. Same with the executive segments that go all the way across. You get essentially no image jump because that's just two bonded pieces of lenses together, and no image jump with progressive bifocals either. Image displacement has to do both with the type of bifocal, but also whether it's on top of a myopic or a minus or a plus lens. So for image displacement, a flat top bifocal acts like base up prism, a round top bifocal acts like base down prism. So here are the four possibilities. Round top plus lens with round top, you see you have base up prism for the lens and base down for the bifocal. So they cancel out, so that's good. Flat top bifocal though, with a plus lens, they're both base up, so then you get a lot of image displacement. For minus lenses, it's the opposite. A round top, you have a lot of image displacement. A flat top, they cancel out, so you minimize image displacement. So for minus lenses, it's easy because the flat top has less image displacement and less image jump. Oops. But for plus lenses, it's a little trickier because the flat top gives you less image jump, but the round top gives you less image displacement. So then it just boils down to, well, what's more important and what bothers people more? And not that many people really complain about image jump because it just happens right at that transition and you're already probably making some sort of a saccade as you go from distance to near. But image displacement could conceivably cause confusion because something is not where you think it is when you're looking through your bifocal, then that can cause you a problem. So generally speaking, we go with the flat tops because image jump is less lesser. Well, we go with the flat top, for the minus lens and a round top for the plus lens to minimize the image displacement. With that said, the reality is that flat top lenses are just more expensive, they're easier to come by, and so pretty much every patient you see is going to have flat top lenses. But if you happen to have a patient who has plus lenses and is complaining of bad image displacement, then you could offer them round top bifocals as an alternative. And then Fresnel prisms are press-on prisms that Fresnel figured out that if you put a whole bunch of little prisms next to each other, optically speaking, that's the same as having a big fat prism. And so it's nice because we can put these on plastic membranes that we then fit onto glasses. And so you can have a patient come in with double vision and go home with single vision with one of these prisms on there. However, you do get a loss in visual acuity because all of these lines cause scattering, you get glare, you get chromatic aberration from the prism, and the plastic itself is hard to clean. And so they're generally speaking a temporary measure that do occasionally, though, still show up out in the real world. So the other thing that prisms do is they can cause chromatic aberration, which I just mentioned. So remember back to refractive index, how I said the speed of light in a substance versus speed of light in a vacuum? Well, it turns out that different wavelengths are slowed differently by the same piece of plastic. So the high energy blue light is charging in there and it gets bent the most, and the lower energy red light glides in and sort of glides on through with a little bit less deflection. So the higher the energy, the more the deflection. And that's why the prisms can create all the colors of the rainbow because of the way that they deflect the light outward at different amounts. And so but which is all very well and good with prisms, but it can be annoying to patients who are wearing prism glasses. And even in non-prism glasses, simple plus lenses also create chromatic aberration. And so high energy blue light is bent more, and low energy relaxed red light is deflected less. So the blue rays of light are focused closer to the lens, and blue and then green and then yellow and then red goes out the furthest. And so the human eye actually this is a model of the chromatic aberration in the human eye, and it's considerable. It's 3 diopter difference in focus at the far ends of the visible spectrum. We think, at least I think, and some of the people think that this chromatic aberration information may have something to do with sort of controlling the growth of the eye and managing growth and controlling myopia. So I think that there's something in there that can help us with myopia, but haven't figured out what. So anyway, but in a more practical sense, we can not use all 3 diopters, but you can use filters to create the red-green test and separate create a spherical difference of about a half a diopter by showing a patient something like this. And so what you do is you show black letters on red and green backgrounds, and then you adjust the sphere. You start by putting all the rays in front of the retina. So you overplus the patient so that red is clearer, and then everything else is also in front. And then, so the patient will say, the red letters are clearer. So if the red letters are clearer, now you can start giving less plus and more minus until they're equally clear on the red and the green side. And then you know you've got the green is as far in front of the eye as the red is behind the retina. And that's optimal focus for yellow and therefore white light. So the duochrome test is used as an endpoint in, for example, refractive surgery, multi-center studies, so that accommodation could be sort of taken out of the equation in that way. So other optics of note. Oh no, that's it for part 3. So we're already to part 4, which is optics in the office. So we're trying to get more and more practical and clinical as we go. So for this last 45 minutes or so, we will try to become even progressively more practical. First, though, just showing you what you've accomplished, I hope, so far, which is that all these scary formulas should now be looking a little friendlier. Delta equals H times D, that's the optical displacement of a lens. U plus D equals V for sure. Focal lengths 1 over power lens and diopters. No biggie. Spherical equivalence, sphere plus half cylinder. Refracting power of a spherical surface, n prime minus n over r, or if you have 2 different spherical surfaces, you take the ratio and you just have n prime minus n in air versus aqueous, or if you have a reflecting instead of a refracting surface, then n prime minus n turns into 2 over r, and then the SRK formula is also helpful to know. So, and then finally, these are all the magnification formulas. It's transverse is image distance over object distance. Axial is the square of the transverse. Simple magnifier is D over 4, or D times the reference distance of 0.25 meters. A telescope, regardless of the type, is power of the eyepiece over power of the objective. And the spectacle lens magnification is 2% per diopter of power. There you go. Those are all that wall of formulas I showed you at the beginning. So then let's move into tips about prescribing glasses, and then a little bit on instruments, and then a tiny bit on just presenting symptoms. So when a patient has a tough retinoscopic reflex, one of the easiest things to do is just to move closer. You get brighter and it's easier to see. You just have to adjust your working distance, right? So if your normal working distance is 2 meters away or a half diopter, and then you move up until you're 10 centimeters away, then you've got like a 10 diopter working distance. So that may be a little rough because 9 versus 1, you'll be off. But at least you can get the cylinder right from up close and get it balanced, and then you back out accordingly. Concentrate on the center of the reflex, contact lens over-refraction when there's irregular astigmatism. Sometimes you'll see a stenopeic slit come up, but I think it's unused enough that we don't have to worry about it too much, but you refract through one, get it the best you can, rotate it 90 degrees, get it the best you can there. That gives you a power cross. Or you can just prescribe pinhole glasses if you want to just get out of it that way. High index lenses, remember we talked about that 1.8 is sort of the highest refractive index, so you can get much thinner lenses because D equals n prime minus n over r. So if you can get n prime minus n bigger, then the radius of curvature doesn't have to be as much to get the same power. So less curved lens is going to be less thick at the edges. And then how do you help a patient like this who wants to improve the appearance of his highly myopic lenses? Well, you can do a cycloplegic refraction, make sure you're not over-minusing them. You can do smaller frames because that curvature, they get thicker and thicker towards the edge, so shrink the size of the frames. Use a higher index refractive index material, like I said. Frames that hide those thick edges can help. And then, so those are sort of the main ones that you go through. If you suggest contact lenses first, it's like in an oral situation, then you'll be told immediately, well, the patient doesn't tolerate contact lenses. So, who's going to have more trouble adjusting to a new contact lens? A pre-presbyopic myope or a pre-presbyopic hyperope? And I used to do the math for this, but it turns out that it's probably best to just sort of memorize it. And that it is that, but I also want you to understand why it should matter. Like, why should it matter whether it's a myope or a presbyope? If they're wearing contact lenses and they're in good focus, why should they have more trouble accommodating? But remember that when the light's coming in parallel rays of light, it's all the same. But but there are different power lenses, first of all, because of the vertex distance. And also it's now diverging light coming in, so you have to accommodate more. And so the vergence of light that passes through a spectacle lens, it's going to change by the time incoming light, by the time it gets to the contact lens. So there's ever-changing vergence. There's difference in power because of vertex distance. And then finally, minus lenses act like base-in prism when you're reading. And so, which helps a myope, and whereas hyperope has like base-out prism, which makes it harder to converge. So putting all of those things together, if you do the math, it turns out that the myope can have a much harder time accommodating through contact lenses than through glasses. They lose this convergence boost, and their accommodative demand is higher because of the things that I said. The hyperope can do better in contact lenses. And again, probably just best to memorize it, but to use this as your sort of mnemonic. So, a 27-year-old patient comes to you a week after you performed a careful refraction, complaining of continued trouble with distance vision, especially or mostly at night. What are some possible causes of what's called night myopia? So first is pupil dilation. Our pupils get bigger at night, and that uncovers the peripheral part of the lens. You have positive spherical aberration, so you become more myopic. Second is the length of the refraction lane. Our lanes are at best 20 feet that we refract, but signs, road signs, they're much further than 20 feet away. If you're fine-tuning your refraction for the exam lane, then you're not fine-tuning for infinity. And so I'll sometimes do a hallway refraction to try to get that nuance, but you can also just subtract an extra quarter diopter off of your final refraction to get the same effect, basically. Third is the lower light levels in the dark cause a shift in our retinal sensitivity towards the blue spectrum. It's the Purkinje shift. And so blue, remember, gets refracted more, so the eye becomes stronger in blue light, and so you end up becoming myopic for that reason. And then finally, this is everything up till now is more optical. This is more accommodative. There's no accommodative targets in the dark or less, so people can dial in their accommodation because they don't have any reference point. The fix for all of these really is just giving a little bit more minus, except for the last one, putting a little bit more minus in the lens, which is fine for a young patient, but a patient who's pre-presbyopic, then you may throw them into not being able to read, so then they might need separate driving glasses that have that extra bit of myopia in them if they complain about it enough. So why doesn't everybody wear progressive lenses? If you look at this Amsler grid, you see there's a marked peripheral irregular astigmatism, and it really depends on the design. There are a lot of different designs that make trade-offs between a narrow channel with less peripheral astigmatism and a wider channel with more peripheral astigmatism, and they all vaunt the advantages of their respective ones. This is, you can tell by the music, this is bad. This is their design. If they don't show it, it's probably more distortion. So that's the narrow channel. Hard to see your breakfast. You might eat the goldfish. Then good music. Now wider. So all these different designs that are out there for the patients to choose from, making that choice. So how does one deal with a patient who's not accepting spectacle correction of astigmatism? So kids, they got cylinder, we just give it to them, whatever it is. But adults, if you change it too much too fast, you can get some fairly bitter complaints. And part of it is this distortion that you can get, but it's usually not just that. It's something a little bit more subtle. And that is that if the left eye sees distortion, say, like this, but then the right eye sees distortion like this, then it's each of the two images are slightly different. And I don't know if you can, I can sometimes do it, or depending on your distance, if you kind of cross your eyes and get them to fuse, then what you'll see is it's a stereogram where that door actually looks like it's falling towards you. Because what are our retinas, what's our brain designed to do? It's designed to take little disparities between the two eyes and build them up into a three-dimensional percept of the world. And so when you have this oblique bilateral astigmatism, you create this disparity. And so they'll say that the floor is coming out at them, the doors are coming out at them, the walls are caving in. And so to fix it, to fix it without changing visual acuity is hard. You can reassure the patient, just try to get them through it. If you reduce the vertex distance, then that can sometimes help. It makes a little bit less distortion. Obviously, contacts help. But if none of those work, then what you have to do is just rotate the axis of astigmatism until it's more vertical or horizontal, so that instead of being obliquely distorted, they're just elongated or narrowed, but you're not getting that binocular phenomenon. Or just reduce the power of the cylinder overall, so that, instead of 2015, they'll be 2025 plus one or so, try to find that balance. That's what I just said there. So why are there different Jackson cross cylinders? Well, when the one that's built into the phoropter is the plus and minus a quarter one, and so when you're refining your refraction, you should actually have the 20/30 letters up there with that one that's built in. But if a patient's vision isn't quite at 20/30, they might not see the difference when you flip them. And so if they have a lower vision, then you can try these higher power Jackson cross cylinders, which they're handheld, and you just hold them over the thing. And I actually just used this last Thursday on a particular patient where we were trying to get him. He didn't see any difference when I flipped him, so I got the one out of the drawer, and he did see the difference, and it changed the angle of cylinder by about 15 degrees or so, from 20 degrees from where I thought it was. So here's a question: which of the following is not a Jackson cross cylinder? Which I don't think I explained. The Jackson cross cylinder is zero spherical equivalent, and it's like you take a plus cylinder and a minus cylinder and you put them 90 degrees away from each other, so that when you flip them, you're enhancing the difference, so that the patient can see the big difference. So here's 5 prescriptions. We have to figure out which one's not a Jackson cross, and we have the combined with symbol here. And actually, I'm not going to go through the answer, but you just have to add up which has zero spherical equivalent and which one is plus and minus cylinder at opposite angles. So like this first one looks okay. I won't go through all of them, but that's plus a half at 90, minus a half at 180. Yes, that's a Jackson cross cylinder. And then there are others to go through. Okay, so finally, wanted to be sure we had time to go through some optical principles of the ophthalmic instruments that we use every day. So we'll go from the trial lens all the way to lasers, and because we already did OCT. So for trial lenses, the trial frames and the trial lenses are built in a certain way to both to optimize the vertex distance and to minimize any sort of spherical aberration. And so we want to have the numbers facing forward in these trial frames, and we want to have them in the back cell. The spherical one should be in the back cell, because that's the proper one for vertex distance. Then the cylinder goes in the front cell, and then any smaller additional lens that goes in front of that. So we can put the trial lenses in trial frames and have patients walk around, and that helps to simulate what they're going to wear. But because base curves are different, apertures are different, even doing this, if you have a big change in cylinder, still it may not perfectly simulate what the patient is going to experience when they get their actual glasses. And speaking of base curves, we have you may or may not have somewhere in your clinic a Geneva lens clock or a lens clock like this. It's got a springy pin in the middle and two fixed pins on the corners, and they measure the curvature of the lens. And so you can find the base curve of the lens, and you can figure out whether the cylinder was ground out of the inner part of the back, or is it on the front of the lens, because that can differ among different opticians. And so you can look for cylinder by checking the two meridians. You can check the front and the back. And the basic idea is a patient comes in and you wrote the exact prescription that they had. Like, you do your whole visit and then they're on their way out the door and they say, "Oh, by the way, doc, can I have a new prescription for glasses?" And you're like, yeah, sure. Let me just write down exactly what's in your old glasses. There you go. And then they come back and say, "These new glasses you gave me, they're terrible. Like, they're nothing like my old glasses." And so one of the things you can do is just check and see if the base curve has changed, because that could make a difference in some cases. So next is a lens meter, and the lens meter is it reads the power of an unknown lens based on the optometer principle. And the optometer principle is something developed to allow for a linear assessment of lens power. Let me try to explain this. So let's say we have a lens meter that doesn't use let's see, this is, yes. So if you had a lens meter that didn't have the optometer principle, and you were just trying to like move a lens back and forth to see when it gets in focus, it's just going to be, high plus lenses, you're going to just barely be able to move them. Minus lenses, you have to put like some other plus neutralizing lens on top. But the optometer principle says that if you take a standard lens, a high plus lens, you put a target at one focal point of the lens, and you put your unknown lens at the other focal point of the standard lens, then that unknown lens, so before you put the unknown lens this target's at 0, you're going to have parallel rays of light, and all is well, it's in focus. Now you put your unknown lens in there, and so if you move this target, so the unknown lens is going to take it out of focus. So in this case, it's a plus lens. As we move it closer to the standard lens, now this diverges the light until it's parallel coming through. So now we know that it's a plus 2.5 lens. If it had been a minus lens, we'd have to move it the other way. And so it converts a nonlinear phenomenon into a linear phenomenon where you can get both plus and minus lenses. So the optometer principle is related to having a standard lens. And all lens meters are based on this. And here's one blow up of a lens meter. Here's the standard lens. There's the target with illumination behind it. Here's where the unknown lens goes. And then to further enhance detection of neutralization, that point when parallel rays are coming out, there's a telescope here with a little reticle on it so that you can know when it's centered as well. And so you can focus it for your eye before you use it. The reticle looks like this. the American cross target anyway. So it should be right in the center. If it's not in the center, there's prismatic power. This is for adjusting sphere. The other triple line is for adjusting cylinder. And when we measure the lenses, we want the temples away from us for the back vertex power, except for measuring bifocal add and segmented bifocals where we want the temples going toward us. So here's what it looks like inside of a lens meter when it's all in focus. But if there's prism induced, then here there's prism, and it looks like it's base up prism because you see how it's deflected up from the center, and these rings have little numbers, like that's a number 2 there, there's a number 1. So that's 1.5 prism diopters of base up prism in this case. If you forget that, the other way to do it is you start within the center and you put your prism up there, and then you can put a neutralizing prism in place to get it centered, and then it would just be here, it's like 3 base out, so you would just, or 5 base out, so then this must be 5 base in of prism in the glasses. But some of the lens meters have a little slot right there for putting in a trial lens, and the ones we use at least have a knob that you can turn to dial in the correct prism power. So let me just show you some of these features in this video I made. So we first want to make sure that the eyepiece is in focus, so I set the lens meter on 0 before I start using it. Then I focus the eyepiece to make sure that the target is in focus. So we set it at 0 before we do anything, and now we look through that's the prism adjustable, we adjust that to 0 too. And now we look through the eyepiece, and we want to make sure it's in good focus. See how the reticle's not really focused, so I sort of dial that in till it's in focus there. Now here comes our unknown lens. Now we turn the knob till it comes in focus. Oh, but I'm moving it around so the optical center is shifting around, so you got to have it in the right spot. And now here's with and without some added prism. So I just flipped in the prism out, in, and out, so you can see that those are the sort of the basics of what you do. Now, how do you handle this problem of the optical center moving around? Like, how do you know how much prism is in there in the glasses? And you can tell that by, you put the glasses on and then you put a little mark right in the center of where the pupil is for each side. So then you're measuring the effective prism power in both sides and get a true measure of what the prism is. Because sometimes we'll have patients whose glasses, like the lens popped out and they popped them in the wrong way, and they can get accidental prism just from having rotated or flipped their optical centers. So this is the best way to do that. What about a retinoscope? A retinoscope is just trying to project diverging light out into the patient's eye so that the eye can focus it and bring it back to you. So you don't want converging light, and so different retinoscopes have different designs. You want to be sure that the sleeve is in the proper direction, and the sleeve should be where there's no place that you can focus the line. If you can focus it anywhere, then it's converging light. You go the opposite way. So when we do retinoscopy, at neutralization, what's happening is the light's going in, and then the light coming back from the eye, if it all fits through the peephole, then we know that the eye is focused exactly on the peephole of the retinoscope. And if it doesn't go through the peephole, then instead of the light, the whole pupil filling with light at neutralization, you're instead going to see either with motion or against motion, but that's for a different lecture. You can actually, there's a nice retinoscopy simulator that allows you to play with this. I have a little bit.ly on there for it if you see that, but there you can also just type in retinoscopy simulator and find it online to play with that yourself. So next is image doubling or optical doubling, and this is something that we often use in ophthalmic instruments. And the idea here is that if you know the distance to an object and you adjust the prism so that the tip of the object, and you can see both the object and image at the same time, and adjust the prism so that the tip of the object is contacting the bottom of the image, is in contact with the top of the object, then you know that the prism is just that. Then you can measure the height of the object. Let me. I think I have a video here. So what I'm doing here is I have a prism bar, and we have this little box, and we want to know how tall is that box, and we can measure it remotely by choosing the prism that allows the object, and like that's too much, that's too far for sure, right there, that one. So that way the bottom of the image is touching the top of the object. And if we now know our exact distance away and the prism power, then we can know how tall the object is. And that allows us to measure objects under high magnification on the eye, even if they're moving around, because you can see the object and image at the same time. You're just adjusting the separation. So we use optical doubling or image doubling in various ophthalmic instruments to make those measurements. One is the Javel-Schiatz tonometer, which is a way to measure corneal curvature. So how do you measure corneal curvature? We'd like to measure the refracting power of the cornea, but we can use the reflecting power of the cornea as a surrogate. So the more curved a cornea is, the more reflecting power it has. The more reflecting power it has, the more it's going to minimize the image. So you project these two boxes, Myers, onto the cornea, and what you see is something like this. So there's the two boxes. Now we're off of the axis of principal meridian of astigmatism here. So you rotate the thing until the Myers line up. In this case, they line up here for this patient. Then you need to, now you're on one of the principal meridians of astigmatism, and this is the endpoint where these touch. But let's say the next patient has the same astigmatism, but a much stronger, steeper cornea, then it's going to shrink the Myers like this. And so then you've got to turn the knob, and it physically changes the separation of the Myers until they touch. And now that's your endpoint, and you read it off the little dial. And then, that's a weak cornea, so that's a flat cornea. It's not as good at creating a small reflection. So that one, you have to separate the opposite direction to get the measurement. And so then you do it in vertical and in horizontal meridian, and then you read it off. You get a radius of curvature number, and you get a diopter number that assumes a certain refractive index. Because remember, all we're measuring here is the reflective power of the cornea, so it's measuring the radius of curvature. So this is the true number. Then this is an inferred diopters of power, assuming that the cornea has a standard refractive index. So that's one kind of a keratometer. The other is the Bausch and Lomb, which is really basically a similar concept, except that it's projecting both vertical and horizontal Myers at the same time, so you can turn two knobs and do all the adjustments at one time. But it's the same thing. You align with axis of principal meridian of the astigmatism, and then if a strong cornea is going to make smaller Myers, a weak cornea is going to make bigger Myers, and you adjust accordingly. So what about the slit lamp? The slit lamp, the key innovation there, and that was Goldstrand when he wasn't off winning Nobel Prize for optical model of the eye. He happened to design the slit lamp as well. That was his version. But the common thing here on all of these slit lamps is that the illumination and the viewing system are on a common pivot point, so that as you move back and forth, the slit stays in focus wherever the oculars are in focus. That was the advance of the slit lamp. So whether it's this design or that one, they all have a common pivot point that's sliding to and fro together. So what he didn't have available to him was the ability to change his magnification, as we can with our slit lamps by changing eyepieces. These are the 10x eyepieces, but there are other powers that you can put in. Also, we have this lever that we can flip, and that allows us to change from low to high. And if you've ever looked on the other side of what happens when you do that, you see that there are these extra objective lenses, more powerful objective lenses. And so when you flip the lever, you're just putting some more powerful objective lenses into the system. or maybe they're, yes, telescope, power of the eyepiece over the power of the objective, so maybe it's the weaker objectives then, right? Anyway, next is applanation tonometer. So an applanation tonometer is a split field plastic prism that separates images while you put pressure against the eye. And the idea here is that when you applanate the cornea to exactly 3.06 millimeter diameter of applanation, then the pressure inside the eye is equal to 1/10 of the force against the eye in dynes. Okay? So, but the endpoint you want is 3.06 millimeters of flattening. So let's say we didn't have a split field prism. We just had a single round applanation tonometer with no split in it. Then here you're probably flattened that, and maybe it has a little line to show you what 3.06 is. So you try to line that up. But you're never going to get it just right because the eye moves around. So let's say it's down here. So that looks close, but that's probably too much. So then you're going to back off on the pressure a little bit. Oh, that's definitely not enough. So now you got to go up. And I think that's about right for the tear meniscus. So that's where you get your pressure, maybe. But who knows? You could be off by quite a lot. So the beauty of the split field prism is that it separates the upper and lower halves by exactly 3.06 millimeters. And so now we have too much force. And so they are clearly separated. So we got to back off. And it's like, whoop, went too far there. Now that's not enough force. And then, there we are, just right. And what are we using? We're using our vernier acuity to complete that line. We're using optical doubling to help us with a measurement, all of the things that I've been talking about to give us a very precise measure of intraocular pressure. So now this is all well and good when the cornea is perfectly spherical, but what happens when the cornea has astigmatism? Well, when you have an astigmatic cornea, then you're not going to have a perfect circle. So there's this little red line that can help you, and I'll explain what that red line is, but first let's just look at what happens. So here's a cornea that's flat horizontally. And so, what are you going to do? You're going to see this and you're going to say, oh, that's not good enough. I got to back off. Even though this actually is the right amount, you're going to back off and so then you're going to get an artificially low reading. Or then you can rotate the applanation tip 90 degrees, and now you say, oh, wait, that's not right. We got to turn it up. Then you get an artificially high reading. So where you really want to measure it is right here, which is 43 degrees away from the principal, from the major axis of the ellipse. And if you do that, then you get just the right pressure. But it turns out, yes, you can do that. And to do that, you put the axis of minus astigmatism on the red line. So if the axis of minus astigmatism is 180, you'd put it to match that red line there. But another way to do it is simply to measure it horizontal, measure it vertical, and take the mathematical average of the two, and that will also give you an accurate pressure. The main thing is to even be aware of it as a problem in the first place. I have had one patient who I was able to take off, who had trauma, high astigmatism, and he was on beta blocker, he was on some topical meds for glaucoma, but when you measured his pressure properly, he actually had fine pressure, and his discs looked good too. So fundus lenses. So, you would think that when you move the slit lamp, common pivot point, so what's the big problem? Why can't you can go to lens, you can go to cornea, iris, lens. Why not just jam it right up against the face and look at the retina? But the problem there is that you have this little 60 diopter lens in front of the retina known as the anterior segment. And so as you try to get closer, those rays of light are converged and you can't get back there. So you need something to do to try to get the to try to get the light back there and therefore to be able to see back there. So one way to deal with it is to put a minus lens in the path to diverge the light on the way into the eye, and that's a ruby lens. So probably nobody, I don't know if people even know what these are anymore, but they give an upright image. They have minimal distortion of magnification and minimal distortion of depth. but they are pretty hard to use compared to some of the other methods. But it's a big minus 55 lens that's in front of the eye. So the other option is a contact lens, a Goldman contact lens, which again sort of neutralizes the curvature of the cornea. It's minus 64 diopters, and it has these little mirrors that allows you to see into the corners as well. But then the completely opposite way to handle the problem is to use a high plus lens instead of a high minus lens. So that's indirect ophthalmoscopy. So then the high plus lens is taking the light that's coming out of the eye, reconverging it to create this intermediate aerial image that you then focus on with the slit lamp. So, when you use the like a 78 or a plus 90 lens, you'll notice that instead of being focused on the eye, you have to back up the slit lamp, because you're backing up to find this aerial image that's somewhere between you and this indirect lens. But it does, if you do the ray tracing, you see it inverts the image. So it's an aerial inverted image with the 90 diopter indirect lens, but a nice way to look at the fundus. And the indirect ophthalmoscope in general is forming this intermediate aerial image. This was an old monocular indirect ophthalmoscope that was in use before Scapin's. Charles Scapin's invented the binocular indirect ophthalmoscope. So, but you see the advantage here is that this condensing lens is capturing more of the peripheral rays, so you're going to get a wider field of view, compared with the direct ophthalmoscope, you get like a 7-degree field of view, but with the indirect, it's more like a 25-degree view because of that capture of the peripheral rays. The thing about it, though, is that and the hard part about the design was you have to somehow optically get both a light source and both of your eyes in through the pupil to see back there. And so the headpiece of the ophthalmoscope has prisms that use total internal reflection, actually, to reduce your pupillary distance so that it'll fit inside of the pupil, and then a light filament that's there too, close to those things. So those three things, optically speaking, fit inside of the patient's pupils. Imagine the first time doing that and getting like a binocular indirect view. That must have been very exciting. So anyway, now you may notice the small pupil scopes and the levers on those, and if you look and see what happens, it's what you might think now that you understand why we have to do that. So let's see what happens when we flip the lever on the small pupil. Up, small pupil, big pupil. Small pupil, big pupil. So it's just moving everything even closer together to fit both of your eyes and the light source through the pupil. So what you don't really want it on small pupil if you don't have to. So you should sort of be paying attention to that to make sure you're not in small pupil by accident, because then you're compromising your depth perception and you're getting a lot more glare and reflections coming back. But when you need it, it's great. But when you don't, then you shouldn't be using it. And here's those prisms that use total internal reflection to reduce your pupillary distance from 60 millimeters down to about 15 millimeters. And that's a normal pupil setting. It's even less in small pupil setting. So if you're going from 60 to 15 millimeters, you're going to get a reduction in your perception of depth. It's going to be down by about 4-fold. So you would think then that everything would look completely flat inside the retina, despite being binocular. But it isn't, and it's partly because of the axial. Remember how axial magnification can distort depth? It's the square of the transverse magnification. So we can do a quick arithmetic here to figure that out. So the magnification when you're doing indirect ophthalmoscopy, this is the transverse magnification. It turns out to be the focal length of the eye over the focal length of the lens, which is the power of the eye over the power of the lens. And so that works out. So for example, for a 20 diopter lens, the transverse magnification is power of the eye or the power of the lens, 60 over 20, which is 3x. So you get 3 times transverse magnification. So if you're looking at something with the indirect ophthalmoscope, 20 diopter lens, looking in the eye, a little tumor is going to be 3 times more across and up in that, 3 times more in diameter than it would be, than it is otherwise. But the axial magnification is the square of the transverse, so it's going to be 3 times more across, but 9 times more in depth. So you're going to get a depth distortion. It's going to look taller or like the tumor will look bigger, more sticking into the eye than it does, than it would in real life if you could just shrink yourself down and go in there. But the eyepieces reduce your depth by 4-fold, so the axial magnification appears to your perception to be about 2.25x versus 3x for transverse. So yes, the 20 diopter lens does flatten the image a little bit compared to if you could just sort of not have to use an indirect ophthalmoscope and use magnifying lenses, but it's only by 2.25 versus 3x. And if you do the arithmetic on the other lenses, the 30 diopter lens does more distortion. The 15 diopter lens has no flattening and no distortion of the image. So you might say, why don't we all use 15 diopter lenses all the time? Well, it doesn't really matter that much because you're used to the 20. That's your baseline. You see the patient from visit to visit, all the thousands and thousands of patients that you see. You build your own, your own network. And so it's not necessary. But if you ever switch from a 20 to a 30 to look at something or vice versa, then you need to be cognizant that your depth distortion is different in the different lenses. So then the last instrument I just wanted to touch on is lasers and laser light. So laser light, what are the features of laser light? And again, we're back to the beginning of the day, sort of, because it's monochromatic, so there's just one wavelength of light, all of it. And therefore, and it's coherent. So all the peaks and valleys line up with each other. It's polarized, so we can manipulate it as we would any polarized light. And those features together also make it directional or non-spreading, so that you can bounce a laser off the moon and back and have it still be together as opposed to any other form of light. So with those features, you can deliver very high amounts of energy into very small spaces. And that's why we use lasers to do damage to treat the eye. And there are 3 ways that we can damage the eye on purpose with the laser light. We can burn it with photocoagulation. We can disrupt it with photodisruption by putting high amounts of energy into small areas, creating like a plasma effect. And so with photodisruption, because you're not having absorption of energy, you create little explosions inside the eye, and so you can cut semi-transparent membranes like the posterior capsule. And then the last is you can break the covalent bonds. You sort of get it, and this is what, like UV laser, it gets into the cells and breaks the covalent bonds that hold things together. So photoablation, you just disseminate the whole. This is breaking the covalent bonds of society. You see, the whole society is falling apart because the laser has broken the bonds that are holding people together. So you can burn it, you can blow it up, or you can insidiously get it from the inside and break the bonds and sublimate the tissue. And that's what the excimer laser does, is it sublimates tissue. So the argon, krypton, red, blue, green, and yellow, red, these are all doing photocoagulation. And as you get into the infrared, though, the only thing that the diode laser can get to, the diode passes through sclera. It's absorbed by pigment epithelial melanin, and it's only the melanin that heats up, and you get like collateral heating of tissues around it. So the only way you burn the retina is by heating up the melanin, like a hot plate under the retina. The YAG is the one that's forming the plasma and creating these little explosion areas and cutting membranes. And then as I said, the excimer laser, it's no heat, it's no plasma, no fire, it's just sublimating tissue by breaking the bonds that hold it together. And speaking of that, this is one of those original. This was one of the Steinert and Pugliafito images of using the excimer laser to put a little to sublimate some corneal tissue. And the thing to think about, to know about that, is that if you now try to come in with a second blast, you're going to have all this in the way, and that's how you get an irregular ablation. So that's why you have to have a fan sort of blowing across the eye to get all that tissue out of the way before the next burst of energy comes in. So finally, in the last 3 minutes or so, maybe I'll run a little bit over, but shouldn't be too much, we'll talk about some of the common problems and likely causes of presenting symptoms. So this sort of shifts us more towards like how something might show up both in an oral exam, but also in real life. Don't forget about that. So this can either be patients complaining of double vision, of bad glasses, I hate my glasses, I can't see well, or I'm getting headaches. So in each one of them, there's overlapping things to think about, but not entirely. So first, double vision. So double vision, we first want to know, is it monocular or binocular? You cover one eye to see if it's monocular, of course. And if it is monocular, then you put up a pinhole, and almost invariably, the monocular diplopia goes away through a pinhole. Every now and then, if there's certain retinal problems or the lenticular irregularity is such that even a pinhole can't make it go away, you may have persistent monocular diplopia through the pinhole. But usually it's even simple refractive error, but more commonly an ocular surface problem, irregular astigmatism, or early cataract that happens to just be the wrong configuration can make this happen. The good thing is that most patients, once you put the pinhole up and show them that they don't have double vision, then they realize that they don't have a brain tumor, and so you don't necessarily have to take any action on it if changing the glasses alone isn't enough. But sometimes that's enough to get a patient to want to have cataract surgery. So what about a patient who says their new glasses are no good? So just like that one I told you about, you wrote the prescription, it was exactly what was in the glasses, handed it to them. So first, just make sure the axis and power are okay, of course. Remember I talked about comparing the base curves. And then look for prism, because we see patients who see double after their new glasses because nobody knew they had prism in their old glasses. It's no one told them, or they don't remember that they were told. Also, there could be inadvertent prism that was put into the glasses because of just the way that the lenses were placed. And trauma to the glasses, I mentioned that case of the kid who was hit with a soccer ball, where the astigmatism is ground. I sort of mentioned that's another lens clock thing. And then there could be just patients particular about certain coatings, certain tints. Just sort of look at the glasses and see if it's something besides the refraction. Also, bifocals, people can get very picky about the segment height, about where exactly it is, the design, the power, more presbyopia, less accommodative ability over time. And then, of course, don't forget to check the refraction. But we do want to look for big changes in the refraction and consider cycloplegic refraction even in adults. I have had adults even close into their 50s who have some element of accommodative esotropia and who are dialing in a lot of accommodation, and we can discover that with a cycloplegic refraction. The fellows who work with me know that every patient gets a refraction, even if they're 20/20 vision in both eyes, because we need to know when they're coming in for a strabismus evaluation if there's something about the refraction that's brought them to multiple doctors and then finally to me. So what if you do your best refraction and they still have poor vision and don't think it's a medical problem? We talked about this a little bit earlier, but don't forget that the pinhole can still diagnose refractive error even after you've done your best refraction. So I will do that from time to time. You do your whole refraction, you're still at 20/30, put the pinhole up. And if they get to 20/20, then there's either still work to do or you have irregular astigmatism. High power Jackson cross, check the eye chart that it's okay. Latent nystagmus, that one throws us off every now and then. Cover either eye, you get latent nystagmus, so your monocular visual acuity is going to be poor in both eyes, but your binocular visual acuity will be normal. And then you can try occluding the eye with a high plus lens. Patients with dry eye sometimes come to see me because of monocular diplopia from the surface issues. So that's another thing to consider, to keep in your mind, in your head. So then finally, the patients will come in with headaches, asthenopia. They don't even know it's their glasses. I did a presentation at the Academy a couple of years ago, the 1 hour refraction. It was this patient who just had, her glasses got scratched, and then she'd been through 5 pairs of glasses, $3,000, and couldn't get away of the asthenopia, the pulling. And so we looked for phorias, we looked for atropia, that didn't work, checked to make sure that the old scratched glasses didn't have prism in them, they didn't. I did a cycloplegic refraction, turned out she was over-minused, and then it turned out that she also had an accommodative insufficiency, so she was 30-something, but had poor accommodation, and that combination of being over-minused and poor accommodation, it was just pushed her over the edge. So all of these things, optical things, can sometimes get you to an answer and help you to help your patients. And again, I know many of you are facing a test, but really what we're looking at here is trying to do the best that we can for our patients. And pretty much anybody can take care of 90% of patients, 95. You don't need to know that much to take care of 90% of your patients. But what are you going to do for those 5% who are struggling, are unhappy, who've been to see many doctors, and are desperate, and who could be helped if you can just figure it out? And so you have to know all of this stuff to be able to help that last group of patients who nobody else can. And it can be very gratifying when you can finally come to the answer for those patients. And so with that, we've done it from 8 a.m. to 2 p.m. Boston time. Thank you to our international visitors. Thanks for Gene Lunderman, who some of you have seen here. And I wish you the best. And I think I have a little.
I see the light in all the colors of the rainbow. Red, orange, and yellow, blue, violet too.